All right, jumping right in, let's take a look at this paper you sent our way. Constant weight polar codes through periodic Markov processes. Gotta admit, just reading the title, it's pretty dense stuff. But I'm getting the feeling there's some really neat math hiding in here.
Oh, yeah, definitely. Constant weight codes, polar codes, they're both kind of at the forefront of coding theory. They have some pretty big implications for, well, how we deal with information in general.
And that's what we're all about here, trying to break this down, get to those cool mathematical ideas.
Exactly.
So our listeners are pretty savvy with math, but just to make sure we're all on the same page, what exactly are constant weight codes? What makes them so special?
Okay, so think about it like this. Digital communication, it's all about sending these strings of zeros and ones, right?
Right.
A constant weight code, it's a set of code words, but with a rule, every code word has to have the same number of ones. Like you're only allowed to send messages if they have, say, 5 on bits.
Huh. Okay, so why do we care about that? What's the benefit of having this strict rule?
Well, it might seem counterintuitive, but that restriction actually helps us with error detection, even error correction. Think about it. If you're expecting a message with, let's say, 5 ones, and you get one with 6.
Something's wrong.
Exactly. You know immediately there's been an error.
Ah, so it's like a built-in check, like a checksum or something. Make sure the data arrived okay.
Yeah, precisely. Now, this particular paper, it's looking at a specific kind of constant weight code where the number of ones is always exactly half the length of the code word.
So perfectly balanced messages.
You got it. And the cool part is they use Markov chains to generate these balanced code words. Markov chains, they're a super useful tool for modeling random processes.
And you know me, I always love a good visual. And look at that, the paper actually has diagrams of these Markov chains. Like figure 1, it shows this chain that generates sequences with a weight of n2.
Right. Each circle, that's a state in the chain. The arrows, they show you how you can jump between states. And each jump adds either a 0 or a 1 to the sequence. You see those labels on the arrows. That tells you if it's a 0 or a 1 being added.
And then, oh, look at figure 2. It's like a simplified version of the same thing. They've merged states with the same phase and weight.
Yeah, it's a good illustration of how you can often represent the same mathematical idea in different ways. In this case, they've made it more compact, but you're not losing any of the important information.
It's all about finding that most elegant, efficient way to describe the math. Now, they also throw in this idea of polarization. Can you give us a quick rundown of what that means in this context?
Sure. So polarization in coding theory, it's this really neat phenomenon. Basically, as you process your data, you do the specific transformation, and the individual bits, they kind of start to separate out. Some become really reliable, some become super unreliable, like you're sifting through and finding the good data, leaving the bad data behind.
So it's almost like you're amplifying the signal, making it more resilient against noise or errors.
Precisely. And what this paper shows is that, yes, you get polarization with these Markov chain-generated constant weight codes, but there's a little catch.
There's always a catch, right?
Right. To make sure this polarization actually happens reliably, you got to fix the starting point of your Markov chain.
So it's like you can wander all over the map, but you got to start at a specific spot.
Yeah, exactly. And the neat part about this paper, they don't just say it, they prove it rigorously. And that's where Theorem 1 comes in. It's the heart of their work.
So Theorem 1, it's like the recipe to make sure this polarization magic actually happens.
Exactly. It lays out all the conditions, all the math you need to guarantee that these constant weight codes, they really do polarize. And this was a big deal because earlier research, it suggested that polarization might not even be possible in these kinds of situations.
So they kind of overturned what everyone thought. Pretty cool. But before we get too deep into Theorem 1 itself, let's take a step back, talk to our listener for a sec. Why should they care about all this high-level math? What's the real-world impact here?
That's a good point. This might seem abstract, but this kind of research, it has huge potential. Think about it. Wireless communication, data storage, even DNA sequencing, anywhere you need to transmit data reliably.
It's all about making sure the information, whether it's bits flying through the air or genetic code, that it arrives safely without errors.
Exactly. And this research, it could lead to more efficient, more robust systems for all of that.
So it's a good reminder that even the most abstract math can end up having a real impact on, well, everything. Okay, let's get into the nitty-gritty now. I'm curious about how they actually define these periodic Markov chains and this phase concept. What's that all about?
Okay, so they start by introducing this idea of a finite state, irreducible Markov process. They call it a FIM process for short. Basically, it's like a souped-up version of a regular Markov chain.
So taking the Markov chain idea and giving it a bit of a mathematical upgrade.
Exactly. With a FIM process, you still have states and transitions between them, each with a certain probability, just like a Markov chain. But a FEM process, it can have a more complex structure, more interesting behavior than a simple Markov chain.
And why the focus on periodic FIM processes? What makes those so special?
Well, the periodicity, that's important because it reflects what we see in a lot of real-world communication scenarios. Think about wireless signals or even how data is stored on a hard drive. You often see repeating patterns in the information.
Right. So understanding how these periodic patterns affect our codes, that's key for designing systems that can actually handle real-world data.
Exactly. Now, the paper, it really gets into the mathematical weeds here, defining all these parameters that might seem a bit intimidating at first, but they're essential for quantifying how information flows in the system, how reliable it is.
Okay, let's break down a few of those. I'm seeing conditional entropy pop up quite a bit. Can you explain what that means in plain English?
Sure, conditional entropy, it's basically a measure of how much uncertainty you have about one thing, given that you already know something else. In our case, it tells us how much information each bit in our sequence is actually carrying.
So it's a way to gauge how informative each bit is, considering what we already know about the other bits in the sequence.
Precisely. Then there's the Bhattacharyya parameter, denoted by z.
Ah, yes, Z. I see it sprinkled all over the equations in the paper.
Right. The Bhattacharya parameter, it's a measure of how different two probability distributions are, kind of like a distance between them. In our case, it tells us how well we can distinguish between the situation where a 0 is sent versus a 1.
So a lower Z value means it's easier to tell those two scenarios apart, meaning a more reliable transmission.
Exactly. And they also talk about total variation parameters.
Okay, add that to our growing list of mathematical tools.
These parameters, they're denoted by this double bar notation, PQ. It's another way to measure how different two probability distributions are. It captures the biggest difference in probabilities that the two distributions assign to any event.
So another tool to help us analyze how the data transforms and how those transformations affect how reliable the transmission is. Now, I'm curious about this phase idea they bring up.
Right. The phase of a state in the FIM process, it's basically a way to group states together based on the patterns they exhibit. Like if you think of the Markov chain as a map, you're categorizing the cities based on certain shared features. Like in figure 1, you see the different phases as horizontal layers in the diagram.
So the phase helps us understand the periodic structure of the FIM process, how those repeating patterns show up in the transitions between states.
Exactly. And with all those definitions, all those tools set up, the authors, they set out to prove their main theorem, the one about polarization.
Theorem 1, the holy grail of this paper.
You got it. And their way of proving it, it's actually quite clever. They break it down into two steps, establishing slow polarization first, and then showing fast polarization.
Okay, I'm picturing a two-act play here.
Yeah, kind of. Slow polarization, that's like the setup. The good data, the bits with entropy close to 0, and the bad data, the bits with entropy close to 1, they start to separate out, but it happens gradually, like a slow sorting process.
And fast polarization, that's where things speed up.
Exactly. Once the slow polarization reaches a certain point, the convergence to either 0 or 1, it happens super fast. It's like hitting the gas pedal on the sorting process. Those reliable and unreliable bits really separate out quickly.
All right, color me intrigued. Let's start with the slow polarization part. How do they prove that?
So what they do is they look at the entropy of each individual bit as it goes through this polar transformation process. The transformation, it's basically a series of steps where you combine the data and shuffle it around. They show that the entropies, they tend to move towards either 0 or 1, meaning the bits are becoming either really reliable or really unreliable.
Like those secrets we talked about, getting passed around. Some become clearer, some just get more jumbled.
Yeah, exactly. And to show how this convergence happens, they use a bunch of lemmas and corollaries. Each one builds on the last, like carefully placed stepping stones leading to the main result.
Okay, let's zoom in on a few of those. Lemma 3, for example, it mentions something called a martingale.
Ah, yes, martingales. They're a really useful tool in probability theory. They help you analyze sequences of random variables where the expected value of the next one, well, it depends on the current one and all the ones before it, but it always equals the current value.
So it's like a fair game, right, where you expect to win on the next bet, on average, exactly what you already have.
Exactly. In lemma 3, it shows that the entropies of the bits, they kind of behave like a martingale in a way. This means they'll eventually converge to a stable value.
So it's saying those secrets, as they get passed around, they eventually reach a point where how clear or how garbled they are, that stabilizes.
Right. Now, lemma 4, it looks at a really important property of the stationary distribution of our FIM process. Remember, the stationary distribution, it's kind of like a long-term snapshot of where the system tends to settle.
Like watching those secret exchanges over a really long time and seeing where the information clusters up.
Precisely. And what lemma 4 shows is that there's a minimum probability for any sequence of 3 states in the process.
So no matter what 3 cities you pick on our map, there's always a decent chance of going between them.
Exactly. This makes sure the polarization doesn't get stuck in some corner of the state space. It guarantees enough mixing, enough randomness to drive the separation of the good bits from the bad bits.
Interesting. So in the lemma 5, it looks like that gets to the heart of how this polar transformation actually affects the flow of information. It analyzes the connection between the entropies of single bits and the entropies of pairs of bits after the transformation.
Oh, so we're basically comparing how uncertain a single secret is versus how uncertain a pair of secrets are after they've been combined and mixed up.
Gotcha.
And the lemma, it uses some clever arguments based on conditioning and the Markov property to come up with inequalities that relate all these different entropies. It's a key step in showing that the polar transformation really does push those entropies towards either 0 or 1. Now, lemma 6, that one digs into the nitty-gritty of the periodic structure of our FIM process. Remember how we broke down the period into a power of 2 and an odd number?
Yeah, it seemed like a pretty specific detail.
Well, it turns out it's crucial. This lemma, it tells us when the difference between the entropies of a single bit and a pair of bits is, well, bounded away from 0.
Meaning, if the uncertainty of one secret is different enough from the uncertainty of 2 secrets, then we know we're getting a certain level of separation between the good data and the bad data.
Exactly. And the proof, they actually use some pretty heavy-duty tools from number theory here. The Chinese remainder theorem, Euler's totient function. It's a great example of how different areas of math can come together to solve problems in fields that seem totally unrelated. Then we have corollary 7. It builds on lemmas 4, 5, and 6 to give us a way to measure how much those entropies move apart during the polar transformation, like putting a number on how well the good and bad data are separating.
I like it, quantifying that separation.
Right. And finally, lemma 8, this one wraps up this slow polarization argument. It shows that those limiting values of the entropies, they really are either 0 or 1 with probability 1. They do a proof by contradiction. They assume there's some chance the entropy is between 0 and 1, and then they show that, well, that leads to something impossible.
So like saying, hey, what if those secrets don't always become perfectly clear or totally garbled? Well, if that were true, then our whole math model would just break down.
Exactly. And that's a classic move in math proof something by showing that assuming the opposite leads to a contradiction. Now, all these lemmas and corollaries, they lead up to proposition 10, the big finale of the slow polarization part. This proposition, it describes what happens to the fraction of bits with entropies below a certain threshold and the fraction above a certain threshold as the block length gets bigger and bigger.
So it's like taking a huge sample of secrets after they've been passed around and looking at how many are super clear versus how many are super jumbled.
Precisely. And proposition 10, it shows that those fractions, they converge to values that are tied to the entropy rate of the FIM process. The entropy rate, it basically tells you how much new information the source is generating. It's like saying as you send more and more secrets, the ratio of clear ones to garbled ones, it settles down to a predictable value, a value that depends on how your secret generating process works.
Makes sense.
And the really important part, proposition 10, it holds even when you take into account the initial phase of the FEM process. So no matter where you start your random walk on that map, the polarization behavior, it's still the same. It's robust.
Powerful stuff. That really lays the foundation for the next part of the story, the fast polarization part. Okay, so we've got the slow polarization down. Now let's get to the fast polarization part. This is where it gets really exciting, right?
Absolutely. Fast polarization is where you see that separation between the good and bad data really take off. And the math they used to prove it, it's quite elegant.
All right, break it down for me. What are the key pieces of this part of the proof?
Well, they use a few powerful tools. One of them is the Cauchy-Schwarz inequality. It's a very fundamental inequality in math. It relates the inner product of two vectors to their magnitudes.
Oh, yeah, I kind of remember that from linear algebra.
Yeah.
How does it apply here?
Right. So in this case, the Cauchy-Schwarz inequality helps them put bounds on the probabilities of certain events that happen during the polar transformation. Remember, we're trying to show that the bits converge really quickly to either being very reliable or very unreliable.
So the inequality helps to um, constrain how those bits behave, how they change as they get transformed and shuffled.
Exactly. They also use properties of the Bhattacharya parameter really cleverly. You'll remember that z, the Bhattacharya parameter, it measures how different the distributions of the received bits are when you send a 0 versus a 1.
Right, right. Lower z means you can tell them apart better, which
Yeah.
means a more reliable transmission.
Exactly. And one of the important lemmas here, lemma 11, it sets an upper bound on the probability of two things happening at the same time, two events related to the polar transformation. And this is where that epsilon parameter comes in.
Ah, excellent. Yeah, it's like a control knob for the polarization speed, right?
Yes, exactly. Epsilon, it's a small positive number, and the smaller you make it, the faster the polarization happens. What lemma 11 shows is that the probability of these two events happening together, you can make it as small as you want by just choosing a small enough epsilon. This basically guarantees that the good data and the bad data separate out quickly.
Okay, so we're using epsilon to fine-tune how fast our polarization engine runs. What's the next step in the proof?
So lemma 12, it builds on lemma 11 and focuses on how the Bhattacharya parameters change after you apply the polar transformation. It shows that these parameters, they either decrease really fast, exponentially fast, or they stay within certain bounds. This means the polarization process is either speeding up like crazy or it's already settled into a stable state.
So we either see those z values plummeting, meaning reliability is improving rapidly, or they're holding steady, meaning we've achieved a certain level of separation and things are staying put.
Right. And then we have lemma 13, which looks at the total variation distance between the distributions of the bits before and after the polar transformation. Remember, the total variation distance, it measures how different two probability distributions are.
Right, it quantifies how much those secret sharing patterns diverge, how much they change as they get passed around.
Exactly. Lemma 13 shows that this distance, it either decreases exponentially fast or it stays bounded. Again, reflecting how the polarization process is progressing. If the distance shrinks quickly, the good data and bad data are becoming more and more distinct.
Okay, so it's another way to see how well that polar transformation is doing its job of sorting the good from the bad.
Exactly. Now, all these lemmas, with all their inequalities and convergence arguments, they lead to the big result for fast polarization, Proposition 14.
All right, lay it on me. What does Proposition 14 tell us?
Okay, so Proposition 14 says that the fraction of bits whose Bhattacharya parameters are below a certain threshold, well, it converges to a value that's related to the conditional entropy of the FEM process. Put simply, as you increase the block length, almost all the bits end up either super reliable with z values near 0 or super unreliable with z values near 1.
So it's like saying, as we send more and more of those secrets, almost all of them end up either perfectly clear or completely scrambled, with very few in between.
Exactly. And just like Proposition 10 for slow polarization, Proposition 14 holds even when you consider the starting phase of the FEM process. This means that this fast polarization behavior is really robust. It doesn't matter where you start.
So no matter where we start our secret sharing game, the outcome is the same. Almost all the secrets end up either perfectly preserved or completely jumbled. All right, so we've got the slow polarization, the fast polarization. It feels like we're ready to tackle Theorem 1, the big result of this paper.
You got it. With both phases of polarization established, the authors have everything they need to formally prove that these constant weight polar codes, they exist and they work for periodic FEM processes.
Okay, let's hear it. What's the essence of Theorem 1 and how do they prove it?
Theorem 1 basically says that if you want a certain level of reliability, any level you want, you can construct a constant weight polar code that will achieve that reliability. And as the block length gets larger, the probability of error goes to 0. It's a powerful statement because it means we can build communication systems that are as close to perfect as we want as long as we use long enough code words.
So if we want to make sure those secrets are almost always perfectly preserved, we just need to make the secret sharing chains long enough.
Precisely. The proof of Theorem 1, it's pretty intricate technically, but the logic is clear. It uses all the results we've talked about, the slow and fast polarization stuff, and ties them together with a technical lemma, lemma 15.
And what does lemma 15 do?
Lemma 15, it sets up some important inequalities that involve the Bhattacharyya parameter and the conditional entropy. It uses ideas about mutually exclusive events and the triangle inequality, a fundamental concept in math that relates the distances between points in a space.
So it's like adding the final set of constraints to our math model, making sure all the pieces fit together just right to get the outcome we want.
Exactly. And with Lemma 15, the authors show that if you choose the parameters of your constant weight polar code carefully, based on the properties of the FIM process, you can get any level of reliability you want as the block length increases.
So it's not just a theoretical possibility. They've actually given us a way to build these codes and get communication that's almost perfect.
That's right. And, this result, it could have a huge impact, not just for communication systems, but for any field where transmitting data reliably is super important.
It really highlights how exploring abstract mathematical concepts can lead to breakthroughs in all sorts of areas. Well, I think we've done it. We've made it through the mathematical jungle of this paper. We've looked at the concepts, explored the proofs, and hopefully we've all come away with a better understanding of how powerful and elegant these constant weight polar codes really are.
It's been quite a journey.
It has. Thanks for being our guide through this intricate mathematical landscape. Your explanations were really clear and insightful.
Happy to do it.
And to our listeners, thank you for sending in this thought-provoking paper. We hope this deep dive has sparked your curiosity and inspired you to keep exploring the amazing world of math and how it connects to the real world, often in unexpected ways. Welcome to another deep dive today. Looks like we're going to be talking about constant weight polar codes.
Yeah.
Specifically, constant weight polar codes through periodic Markov processes.
That's it. It's a fascinating area, and these codes aren't just some mathematical curiosity.
Right.
They have this huge potential for ensuring reliable data transmission. I'm sure you can appreciate that.
Yeah, definitely.
Given all your interests. What's really interesting about this paper is how it connects those codes to Markov chains.
Yeah.
Did you see that coming?
Not at all. It's not the first connection that springs to mind, right?
Right.
But before we get to that Markov chain surprise,
Yeah.
let's make sure we're all on the same page about the basics.
Sure.
What is the constant weight code, and why would we want to constrain code words that way?
Okay, yeah. So at the most basic level, a constant weight code is one where every code word, every valid code word has the same number of 1 bits.
Okay.
And you can think of it as introducing redundancy into our code. And why do we want to do that? Well, it plays a crucial role in error correction, which is essential for reliable data storage and transmission.
Right. So it's like a built-in safety net. Kind of.
Yeah, exactly.
To help catch those errors that can sneak in.
Yes.
Okay, cool. So let's get to the part that really blew my mind. Using a periodic Markov chain to generate the codes.
Okay.
Figure 1 in the paper visualizes this so well. It's like a roadmap for building a code.
Yeah. Figure 1 is key.
Yeah.
Each circle represents a state in the Markov chain,
Uh-huh.
and the arrows show the possible transitions between those states.
Right.
The really clever part is how they've designed these transitions to make sure that the output, the sequence of zeros and ones, always maintains that constant weight property.
So each step along the chain is like adding another bit to our code word.
That's right.
And the structure of the chain itself guarantees that we stay within the rules of a constant weight code.
Yeah, exactly.
Okay, cool. I did notice that the example in figure 1 creates codes of weight N2. Is that a limitation of this technique, or can it be generalized?
No, it's not a limitation at all. The authors, they chose to focus on that N2 case just for clarity.
Right.
But the paper clearly states that this approach can be extended to generate codes with other weights as well.
Okay.
It's like a blueprint that you can adapt,
Right, so it's more like a general recipe, not just a single recipe.
Exactly.
Okay, cool. Now on to the part that seems crucial, but I'm a bit fuzzy on the why.
Okay.
The paper makes a big deal about fixing the initial state of the Markov chain.
Yes.
What's the significance of that choice in terms of polarization?
Great question. That goes right to the heart of how these codes achieve their remarkable properties.
Okay.
Remember, our goal is to create codes that exhibit polarization. That means the bits within a code word effectively split into two groups.
Okay.
Those that are highly reliable and those that are less so.
Right.
And fixing the initial state is what allows us to guarantee that polarization will occur within this framework of this Markov chain construction.
So it's not just an arbitrary choice.
No.
It's essential for setting the stage for polarization to happen down the line.
Exactly.
Okay. But let's rewind for a second. Why do we even care about polarization?
Okay.
What makes it so special?
Polarization is the secret sauce that makes these codes so powerful.
Okay.
When we have polarization, we can focus our efforts on protecting those highly reliable bits, the ones that we know are very likely to be transmitted correctly.
Okay.
This leads to incredibly efficient encoding and decoding schemes.
It's like knowing which soldiers are your best fighters and sending them out with the strongest armor, right?
Exactly.
Okay. Now, you mentioned the proof of polarization.
Yes.
I know our listener is super comfortable with math.
Okay.
So, should we dive into the details of how the paper demonstrates this crucial property?
Absolutely.
Okay.
The authors construct this really beautiful and elegant proof leveraging some pretty powerful tools from probability theory.
Yeah.
They start by defining a random variable, let's call it Wn, which represents a particular bit at the nth stage of the encoding process.
So Goin is like a snapshot of a single bit as it evolves through this Markov chain construction.
Exactly.
Right.
Now, here's where the martingale concept comes in.
Okay.
They show that this sequence of random variables, this W, forms a bounded submartingale.
Okay. And just to remind me, what's a submartingale?
Yeah, so a submartingale is a sequence of random variables where the conditional expectation of the next value, given all the previous values, is at least as large as the current value.
Right.
It's like a game where the odds are slightly in your favor. You expect, on average, for your winnings to increase over time.
Okay.
And that's really crucial here because it allows us to apply this powerful theorem, the martingale convergence theorem,
Okay.
which guarantees that this bounded submartingale, W1, will converge to a limiting random variable W.
So they've shown that as our encoding process progresses,
Right.
the behavior of these individual bits settles down to a specific predictable pattern represented by that limiting random variable. That feels significant.
And it is. It gets even more interesting.
Okay.
Lemma 8 in the paper proves that this limiting random variable, this W, can only take on two possible values, 0 or 1.
It's all or nothing then for these bits.
Yes.
They either converge to a state of perfect reliability, represented by 1,
Right.
or they end up in the unreliable camp, represented by 0.
Yes.
This is where the polar codes really shines through, right?
Exactly. That all or nothing behavior, that is the essence of polarization.
Okay. But we're not done yet, are we?
Not quite.
We've shown that the convergence happens,
Yeah.
but we need to establish that this polarization occurs quickly.
Right.
And this is where the paper gets into the details of how the polarization process unfolds over time.
Yes.
And it's pretty intricate, I gotta say.
Yeah, it is.
So let's try to break it down step by step.
Yeah.
Where do they go from this idea of a limiting random variable that takes on only two values?
So they use a series of lemmas and corollaries to carefully analyze how the distribution of W changes as n increases, which corresponds to progressing through the stages of our encoding process.
Right.
A key insight is that the polarization process starts slowly,
Okay.
but then it accelerates rapidly.
Okay, so at first those bits are kind of meandering, not sure which camp they'll end up in.
Right.
But then something clicks and boom, they rush towards either extreme reliability or unreliability.
That's a great way to visualize it.
Okay.
So corollary 7,
Yeah.
it establishes that the difference between the conditional expectation of Wn, given the previous values, and the actual value of W shrinks as Nn increases.
Okay.
This means the process is initially slow, but then things speed up.
What happens then?
Corollary 10 and proposition 14 work together to demonstrate this rapid acceleration.
Okay.
They essentially show that once a bit starts leaning towards reliability or unreliability, it quickly commits and polarizes towards that extreme.
It's like a snowball rolling down a hill. Starts small, but then it gathers momentum and becomes unstoppable.
Perfect analogy. And all of this, remember, is happening within this specific structure of the Markov chain that we saw in Figure 1.
Yeah.
Those state transitions and that careful choice of the initial state, that's what underpins this entire polarization process.
It's amazing how it all ties together. We started with this abstract idea of constant weight codes, ventured into the world of Markov chains, and now we've arrived at this powerful concept of polarization. It feels like we've climbed a mathematical mountain.
Indeed. And the view from the summit is pretty rewarding.
Yes, but before we take in that view, there's one more piece of the puzzle we need to discuss.
Okay.
The final theorem
Uh-huh.
that ties all of this together.
Yes.
Theorem 1. It feels like the grand finale of this mathematical symphony.
It is. And a grand finale it is.
Why?
Theorem 1 formally establishes the existence of constant weight polar codes with some really desirable properties.
Okay.
Specifically, these codes achieve a rate approaching something called HXHXY.
Okay.
And their probability of error vanishes as the code length increases.
Whoa, hold on. Let's unpack those terms for our listeners who might not be coding theory experts.
Okay.
What does HXY represent?
Yeah. You can think of it as the theoretical speed limit
Okay.
for transmitting information reliably over a given channel.
Okay.
HX represents the entropy of the source,
Okay.
which is a measure of the randomness or uncertainty of the messages that we're trying to send.
So the more random our messages, the higher the entropy.
Exactly. And
Okay.
HXY, that's the conditional entropy,
Oh.
which measures how much uncertainty remains about the source after we've observed the received signal, Y.
Okay.
So HXY represents how much information we can squeeze through the channel given its inherent noise and limitations.
It's like figuring out how much water we can actually get through a pipe, accounting for any leaks or blockages.
Exactly.
Okay.
And Theorem 1 says these constant weight polar codes, they get amazingly close to that theoretical limit.
Wow.
Isn't that amazing?
That's incredible. But what about that vanishing error probability? That sounds pretty impressive too.
It is. That's where the real power of polarization shines through.
Okay.
The theorem guarantees that as we make our codes longer, the chance of making an error becomes incredibly small.
So it's like having a super accurate GPS that gets even more precise as you zoom in on the map.
Right.
The longer the code, the less likely we are to get lost in the noise.
Precisely. And this combination of near optimal rate and vanishing error probability is what makes constant weight polar codes so exciting for practical applications.
It's like they've found the holy grail of coding theory.
It really is.
We started with this simple constraint of constant weight.
Yeah.
And we've ended up with these incredibly powerful codes that push the limits of reliable communication.
It's a testament to the beauty and power of mathematical thinking.
Absolutely. Well, before we move on to the practical implications,
Okay.
let's take a moment to recap what we've learned so far. We've explored the construction of constant weight polar codes through this fascinating lens of periodic Markov chains.
Yes. And we've seen how that careful choice of the initial state sets the stage for polarization.
Right.
Where the bits in our code words effectively sort themselves into highly reliable and less reliable groups. We've also delved into that intricate proof of polarization,
Yes.
using concepts like martingales and convergence to establish this remarkable property.
Yep. And Theorem 1, the grand finale,
Yes.
guarantees the existence of these codes with near optimal rate and vanishing error probability.
It's been quite a journey,
It has been.
and we're only just getting started.
Indeed. But for now, let's take a pause here.
Okay.
When we come back, we'll explore the real-world implications of these constant weight polar codes
Sounds good.
and delve into some of the exciting possibilities that they unlock for things like data storage, transmission, and beyond.
I'm excited.
Me too. It's going to be good.
Yeah.
Welcome back. I don't know about you, but after that deep dive into the proof of polarization, I'm ready to see how all of this theoretical magic translates into real-world impact.
Yeah, an excellent point. The beauty of this research is that it's not just elegant mathematics. It has the potential to revolutionize how we handle data.
Okay, let's get specific then. Theorem 1 gave us these really impressive guarantees about rate and error probability. What does that mean for, say, someone who wants to send a video over a noisy internet connection?
Well, for starters, it means that that video is going to arrive much faster and with far fewer glitches. Remember that HXY term we talked about?
Yeah.
That's like the theoretical limit on how much information we can reliably squeeze through a channel. These codes come incredibly close to achieving that limit.
So they're like race cars pushing the boundaries of what's possible in terms of data transmission speed.
Exactly. And the vanishing error probability means that even if there's interference on the line, that video is highly likely to arrive intact.
That's a game changer for anyone who's ever had to deal with choppy video calls or buffering issues. But data transmission is only one side of the coin. What about data storage? How does this research impact that realm?
That's where the robustness of these codes really shines. Think about hard drives, for instance. They're constantly susceptible to errors due to physical wear and tear.
Right, so those little magnetic bits on the disk can get flipped or corrupted over time.
Precisely. But by using constant weight polar codes, we can introduce this level of redundancy that makes that data much more resilient to those errors.
It's like having a backup system in place, right?
Yeah.
Ensuring that even if some bits go haywire, we can still recover the original information.
That's a great analogy. And the beauty is that these codes don't just protect against random errors, they can also handle like bursts of errors that might occur due to a scratch on the disk or a power surge.
So it's like having a shield that can deflect both small arrows and large projectiles.
Exactly. This makes them incredibly valuable for applications where data integrity is paramount, like archival storage or critical systems where data loss is simply not an option.
Okay, I'm seeing the potential here. Faster downloads, more reliable storage, and a future where dropped calls and corrupted files are things of the past. But let's not get ahead of ourselves. There are always challenges in translating theoretical breakthroughs into real-world technologies, right?
Absolutely. As with any new approach, there are practical considerations to address, and one of the key challenges is computational complexity.
Yeah, I was wondering about that. Encoding and decoding these codes probably involves some serious number crunching, especially as the code length increases.
You're right. As we strive for those near optimal rates and vanishing error probabilities, the algorithms involved can become quite computationally demanding. So there's a lot of ongoing research focused on finding efficient ways to encode and decode these codes, making them more practical for real-time applications.
So it's like having a powerful engine, but now we need to streamline the transmission to get the most out of it.
Exactly.
What are some of the approaches researchers are exploring to tackle this complexity challenge?
Well, one avenue is to develop specialized hardware that's tailored specifically for these codes.
Okay.
This could involve designing custom chips or circuits that can perform the encoding and decoding operations much faster than general-purpose processors.
So it's like having a dedicated lane on the highway just for these codes to zip through, bypassing all the traffic.
That's a great way to think about it. Another approach is to develop more efficient algorithms that can take advantage of the specific structure of these codes.
Okay.
For example, researchers are exploring ways to exploit the symmetries that are inherent in that Markov chain construction to reduce the number of computations required.
It's like finding shortcuts in a maze, using our knowledge of the layout to navigate it more efficiently.
Exactly. And there's also a lot of work being done on approximate decoding techniques,
Okay.
where we sacrifice a tiny bit of accuracy in exchange for a significant speedup.
So it's like saying, we don't need to get the answer exactly right, just close enough for practical purposes.
Yeah.
That's a clever trade-off.
And in many applications, it's a perfectly acceptable trade-off. For example, if we're streaming a video, a few lost pixels here and there are unlikely to be noticeable.
Right, okay. So we've got researchers working on the hardware and software fronts to make these codes more manageable for our devices. What other areas of research stem from this work? Where else might these codes find a home?
One exciting area is in distributed storage systems, where data is spread across multiple devices or servers.
Okay, so instead of having all our eggs in one basket, we're distributing them across multiple baskets to reduce the risk of catastrophic loss.
Precisely. And in these distributed systems, constant weight polar codes can be used to ensure data redundancy and resilience in a very efficient way.
It's like having multiple backup copies of our data strategically placed throughout the system so that even if one device fails, we can still retrieve the information from the others.
That's right. And this has huge implications for cloud storage services where reliability and data availability are paramount.
For sure, yeah. Another area that comes to mind is wireless communication, especially with the rise of 5G and beyond. Those networks are all about handling massive amounts of data at high speeds.
You're spot on. These codes are well suited for the demanding conditions of wireless channels, which are notoriously noisy and prone to interference.
So it's like giving our data a robust suit of armor to navigate the treacherous terrain of wireless signals.
Precisely. Their ability to correct errors and approach channel capacity makes them ideal for ensuring reliable communication in these challenging environments.
This is fascinating stuff. I feel like we're only scratching the surface of what these codes can do.
Right.
Are there any other potential applications that researchers are exploring, maybe some that are a bit more outside the box?
Absolutely. One intriguing avenue is in the field of DNA sequencing, where the goal is to accurately read the genetic code.
Wait, how do codes tie into DNA sequencing? That sounds like a huge leap.
It might seem surprising, but DNA sequencing actually shares some fundamental similarities with communication systems. We're essentially trying to transmit genetic information from the biological realm to the digital realm,
Okay.
and that process is inherently noisy and prone to errors.
So those A's, T's, C's, and G's are like the bits in our code words.
Exactly. And just like in communication systems, we need robust codes to ensure that we're reading the genetic code accurately. Constant weight polar codes, with their error-correcting capabilities, have the potential to revolutionize the accuracy and efficiency of DNA sequencing.
That's mind-blowing. It
Well,
seems like the applications of these codes are only limited by our imagination.
I completely agree. This research has opened up a Pandora's box of possibilities. I'm excited to see where it leads us in the years to come.
This has been an incredible deep dive. We've gone from the theoretical underpinnings of these codes to a whirlwind tour of their potential impact on data transmission, storage, and even fields as diverse as DNA sequencing. I'm feeling pretty inspired, but I think we need a moment to digest all of this before we jump into the final part of our discussion.
I concur. Let's take a brief pause and gather our thoughts. When we return, we'll delve into some of the broader implications of this research and explore a few intriguing questions that have been swirling in my mind.
Welcome back. We've covered a lot of ground in our deep dive into constant weight polar codes. From Markov chains to vanishing error probabilities, it's been quite a journey.
And we've seen how this seemingly abstract mathematical concept has the potential to revolutionize everything from, video streaming to DNA sequencing. But before we wrap up, I'd like to kind of step back and consider some of the broader implications of this research.
I'm all ears. What's been swirling in your mind?
Well, one thing that struck me is how this work highlights the interconnectedness of different fields of mathematics.
We've seen how concepts from probability theory, information theory, and even linear algebra, they all kind of come together in this really elegant framework.
I feel like they're different threads woven together to create this beautiful tapestry.
Exactly. And it makes me wonder what other unexpected connections are waiting to be discovered.
Right.
Perhaps there are insights from other areas of math that could further enhance these codes or lead to the development of entirely new coding schemes.
That's a fascinating thought. It's like we've opened a door to a whole new landscape, and who knows what wonders await us out there.
Another aspect that I find intriguing is the kind of broader philosophical implications of this research.
Okay.
These codes, in a way, they embody our ongoing quest to impose order on the inherent chaos of information.
That's a profound way to put it. We're constantly battling against noise, errors, right, and that tendency for information to degrade over time.
Precisely. And these codes represent like a powerful tool in that battle.
Allowing us to transmit and store information with this, remarkable reliability. It makes me wonder about the limits of this quest.
Okay.
Can we ever truly achieve perfect information transmission and storage?
Right.
Or will there always be some inherent uncertainty that we must contend with?
Those are deep questions, and I don't know if we have the answers yet.
Yeah.
But it's inspiring to see how mathematicians are pushing the boundaries of what's possible.
Absolutely.
Constantly striving for more efficient and robust ways to handle information.
Indeed. And this particular research on constant weight polar codes, it's a testament to that spirit of innovation.
Right.
It's a reminder that even in a field as, well established as coding theory, there are still groundbreaking discoveries to be made.
Speaking of groundbreaking discoveries, there's one aspect of this paper that we haven't really discussed in detail.
Okay.
But I think it deserves some attention.
Yeah.
Remember how the paper focuses on binary codes?
Yeah.
Those working with zeros and ones?
Yeah, the classic foundation of digital communication.
But the world is rarely black and white, isn't it?
Right.
What about codes with larger alphabets? Those that use more than just two symbols? Could similar techniques be applied in those realms?
That's a question that's been on my mind as well.
Yeah.
While the paper doesn't explicitly address this, I believe it opens up a whole new avenue for exploration.
Right.
Imagine the possibilities if we could extend these concepts to, ternary codes using zeros, ones, and twos, or even quaternary codes with 4 symbols.
It's like expanding our palette from black and white to a full spectrum of colors.
Exactly. Such codes could potentially offer even greater efficiency and robustness, allowing us to pack more information into each code word and further enhance error correction capabilities.
But I imagine there are also challenges associated with venturing into these uncharted territories.
Well, of course. One obvious hurdle is the, increased complexity.
Mm.
As we expand that alphabet size, the number of possible combinations and transitions within the Markov chain grows exponentially.
Right. That visual representation we discussed earlier, figure 1 in the paper, would become a tangled web of connections.
Indeed. And that complexity would ripple through the entire process from constructing the codes to designing efficient encoding and decoding algorithms.
Right.
We might need to develop entirely new mathematical tools and techniques to tackle these challenges.
It's like exploring this vast, uncharted jungle where we'll need to forge new paths and overcome unexpected obstacles.
Another challenge arises from the nature of the constant weight constraint itself.
Okay.
With binary codes, it's pretty straightforward. We simply restrict the number of ones in each code word.
Right.
But with larger alphabets, we have, more degrees of freedom.
So instead of just counting ones, we might need to consider the distribution of different symbols within the code word, like ensuring we have a balanced mix of colors in our painting.
Precisely. Finding the optimal distribution for different applications and channel characteristics. That would be a crucial area of research.
Yeah.
We might need to develop new metrics and criteria for evaluating the performance of these codes.
It sounds like extending this research to larger alphabets is a daunting but incredibly exciting endeavor.
I couldn't agree more. It's a challenge worthy of, the brightest minds in coding theory and related fields. Who knows what breakthroughs await us as we venture into these uncharted waters?
Well, on that note of boundless possibility, I think it's time to wrap up our deep dive. We've journeyed from the theoretical foundations of constant weight polar codes to a glimpse of their potential impact on our technological world
Right.
and even our understanding of the universe itself.
It's been a privilege to share this exploration with you and our listener. May this deep dive inspire further curiosity and a thirst for knowledge that knows no bounds.
Thank you for joining us on this intellectual adventure. Until next time, keep those minds engaged and those questions flowing. All right, let's dive into this research paper on constant weight polar codes.
Yeah.
Specifically the one titled
Mhm.
Constant Weight Polar Codes Through Periodic Markov Processes.
Okay.
I'm really curious to see how they're using
Right.
Markov chains to create these codes.
Mhm.
Just the title alone has piqued my interest.
Interesting.
What do you think is the most fascinating aspect of this paper?
Well, I think what's captivating about this paper is its focus on
Alright.
addressing a fundamental communication challenge,
Huh?
reliably transmitting information when the weight of your message is restricted.
Okay.
It delves into the realm of weight-constrained codes,
Right.
which are vital for applications like data storage and
Yeah.
secure communication, where maintaining a specific weight in the transmitted sequences is crucial.
Okay, so before we go any further,
Sure.
can you remind me about the concept of weight in this context?
Certainly in this context, the weight of a message refers to the number of 1 bits in the sequence.
Got it.
For instance, a message sequence like 1011 would have a weight of 3.
Okay.
The paper explores scenarios where the weight of these sequences needs to be kept constant, which introduces unique challenges for encoding and decoding information.
That makes sense.
Yeah.
Now, the abstract of the paper mentions that
Yeah.
traditional polarization techniques,
Right.
which have been very successful in some areas,
Mm.
don't always work for all Markov processes.
That's right.
Why is that?
That's a critical point.
Yeah.
Traditional polarization techniques rely on the inherent structure of certain types of codes
Okay.
to achieve polarization,
Right.
which is the process of separating the reliable parts of a message
Yeah.
from the unreliable ones.
Makes sense.
However, when dealing with Markov processes that don't exhibit the necessary properties,
Okay.
those techniques fall short.
So what's the key insight the researchers bring to the table
Right.
to overcome this limitation?
The researchers discovered that by strategically fixing the initial state of a periodic Markov chain, you can actually induce polarization, even in those cases where traditional methods fail.
Okay.
This is a significant breakthrough because it opens up possibilities for constructing efficient and reliable codes in a broader range of scenarios.
That's a pretty neat trick.
Yeah.
But before we get into the details of their approach,
Sure.
can you quickly refresh my memory on what a Markov chain is?
Okay.
Sometimes I forget the specifics.
A Markov chain is a mathematical model
Okay.
that describes a sequence of events
Right.
where the probability of each event depends only on the state attained in the previous event.
Got it.
Imagine a simple weather model. If today is sunny,
Mm-hmm.
there's a higher probability that tomorrow will also be sunny,
Right.
but there's still a chance of rain.
Makes sense.
Each day's weather in this model is a state,
Okay.
and the transitions between these states
Okay.
are governed by probabilities.
I like that weather analogy.
Yeah.
It makes the concept much clearer.
Yeah.
So, in essence, the researchers are saying that if we start our weather system in a specific state,
Exactly.
we can achieve this polarization effect that's so crucial for reliable communication.
Yeah.
It seems almost too simple to be true.
It might seem simple,
Yeah.
but the implications are far-reaching.
Okay.
This insight allows for the construction of constant weight polar codes using a wider range of Markov processes than previously thought possible.
All right, let's get into the specifics.
Sure.
They provide a visual example in Figure 1, right?
Yes, they do.
What can you tell me about that?
Figure 1 in the paper illustrates an irreducible Markov chain that generates sequences with a constant weight equal to half their length.
Okay.
It's like a roadmap for our code, showing us all the possible paths our information can take.
I see. So you start at a specific state labeled Y.
You got it.
And then follow the arrows.
Right.
What do the blue and red arrows represent?
Nice. The blue arrows represent a 0 in our message sequence,
Okay.
while the red arrows represent a 1.
Got it.
The key here is that you must always begin and end at the Y state.
Right.
This constraint ensures that the final message sequence will have the correct weight,
Okay.
which in this case is half the length of the sequence.
That makes sense.
Yeah.
Now, they mentioned that even though this Markov chain generates only a subset of all possible weight 2 sequences of length, 4, each of those sequences has an equal probability of 16.
Right.
What's the significance of that?
This equal probability is a result of the careful design of the Markov chain.
Okay.
It ensures a balanced distribution of the generated sequences,
Right.
preventing any particular sequence from being favored over others.
Right.
This balance is essential for achieving reliable communication.
Now, Figure 2 explores the trade-off between the number of states in the Markov chain and the proportion of weight-constrained sequences it can generate. Can you elaborate on that?
Certainly, as you increase the number of states in the Markov chain,
Right.
you gain more flexibility in generating weight-constrained sequences.
Okay.
You can imagine that a more complex map allows for more diverse paths.
Okay.
However, this flexibility comes at the cost
Right.
of increased complexity in the encoding and decoding processes.
So it's a balancing act between flexibility and complexity.
Exactly.
If I'm working with a specific sequence length that's not a multiple of the period,
Right.
do I need to be mindful of anything in particular?
Absolutely.
What's that?
You need to pay close attention to the weight of the final state in the Markov chain.
Got it.
If you're aiming for a specific overall weight in your final message, you need to make sure the final state you land on contributes the right amount to that total weight.
That's a great point. It's like making sure the last piece of a puzzle fits perfectly to complete the picture.
Yes.
Now, the researchers didn't limit themselves to a fixed weight of half, did they?
No.
What else did they do?
They extended their approach to generate sequences with any desired weight, or even a range of weights, by adjusting the period of the Markov chain and the constraints on the initial and final states.
That sounds impressive.
Yeah.
Now, let's shift our focus to the mathematical foundation of this paper.
Okay.
They have a section titled Setting and Main Theorem,
Yes.
which lays out the groundwork for their analysis, right?
Exactly. In that section, they introduce notations and definitions for a strictly stationary process, which is a process where the statistical properties don't change over time.
So what are some of the key concepts they define in this section?
They define terms like conditional distribution, which tells us the probability of an event happening given that another event has already occurred.
Okay.
They also define the Markov property, which states that in these processes, the future only depends on the present state, not the entire history of past states.
Can you give me an example of the Markov property in action?
Imagine you're tracking the movement of a chess piece on a board.
Okay.
The Markov property states that the piece's next move only depends on its current position.
Got it.
not the sequence of moves that brought it there.
Okay.
Its past doesn't influence its immediate future.
That's a helpful way to visualize it.
Yeah.
They also mention this concept of phases, right?
Yes, they do.
What are those?
Think of phases as distinct groups within our Markov chain,
Okay.
where states within a phase can transition to each other,
Right.
but not to states in other phases.
Got it.
It's like dividing a play into different acts.
Okay.
Each act has its set of characters and possible outcomes.
All right. So we've got conditional distributions,
Okay.
the Markov property,
Mm-hmm.
and these phases dividing up our Markov chain.
Right.
What other mathematical concepts do they lay out in this section?
They introduce the concepts of
Okay.
conditional entropy, Bhattacharyya parameter,
Okay.
and total variation parameter.
All right.
These parameters play a crucial role
Okay.
in proving polarization theorems, which are the mathematical backbone
Right.
of the paper's results.
Can you elaborate on those parameters?
Sure.
What do they measure?
Conditional entropy measures the average uncertainty of a random variable
Right.
given the value of another random variable.
Okay.
The Bhattacharyya parameter measures the similarity between two probability distributions.
Got it.
It's used to quantify how easily we can distinguish between two different signals.
Right.
Finally, the total variation parameter measures the distance between two probability distributions.
Okay, so they have all these parameters defined.
Right.
What do they do with them?
These parameters are used to formally describe the phenomenon of polarization, which, as we discussed earlier, is the process of separating the reliable and unreliable parts of a message during encoding and decoding.
Right, and that separation is key to achieving reliable communication.
It is.
Now, they have a couple of equations, 1 and 2, in this section.
Right.
What are those about?
Those equations define the entropy rate of the process.
Okay.
You can think of entropy as a measure of uncertainty or randomness.
Right.
In this context, the entropy rate represents the average amount of information being generated by our process over time.
So are these equations calculating the same thing?
Not exactly. Equation 1 calculates the entropy rate without taking the states themselves into account, while equation 2 includes them. These two perspectives provide a complete picture of the information flow in our system.
Got it. They then introduce theorem 1, which seems to be a central result of this paper.
It is.
What can you tell me about this theorem?
Theorem 1 is a key result that connects the theoretical framework they've established to the practical application of polar coding using the Honda-Yamamoto scheme, which is a specific technique for constructing polar codes.
What does this theorem actually state?
It states that using their approach, we can construct polar codes that achieve a rate approaching a specific value.
Got it.
Which is the difference between the two types of entropy rates we just discussed.
Right.
What's remarkable is that these codes can achieve a vanishingly small error probability, meaning they're incredibly reliable.
That sounds fantastic.
It is.
But is there a catch?
There's always a trade-off.
Okay, what's the trade-off?
The theorem also points out that the complexity of encoding and decoding these codes depends on the number of states in our Markov chain.
Right.
So if we want more flexibility in generating weight-constrained sequences, we might have to pay the price of increased complexity in implementation.
That makes sense.
Yeah.
There's no such thing as a free lunch, right?
Sure, right.
They also mention an event.
Yes.
Denoted as hashtag in this theorem.
Yes, they do.
What's the significance of that?
The event hashtag captures the specific constraints on the initial and final states of our Markov chain.
Right.
Remember, the researchers discovered that fixing the initial state is key to achieving polarization.
Right.
This event formalizes those constraints.
Okay, so we have this powerful theorem that promises reliable codes with a specific rate. But how do we know this theorem holds true?
That's a great question.
That's where the proof comes in, right?
Exactly. The paper then dives into the proof, the theorem 1.
And what's the first step in their proof?
The first step involves factorizing the period of the Markov chain, breaking it down into two parts.
Got it.
Which is a power of 2, and q, which is an odd number.
Why is this factorization important?
It might seem like a minor detail,
Yeah.
but it's a crucial step in the proof.
Okay.
The researchers cleverly use this factorization to demonstrate that both slow polarization and fast polarization occur
Okay.
when you fix the phase modulo d of the initial state.
What exactly do they mean by slow polarization and fast polarization?
Okay.
Can you elaborate on these concepts?
Imagine you're sorting through a pile of coins, trying to separate the heads from the tails.
Okay.
Slow polarization is like gradually identifying which coins are likely to be heads and which are likely to be tails. Okay.
Fast polarization is like suddenly discovering a magnet
Got it.
that quickly pulls all the heads to one side,
Right.
making the separation process much faster.
So in the context of our codes, slow polarization gradually identifies the reliable and unreliable parts of the message.
Precisely.
While fast polarization accelerates the separation process.
Yes.
Making the reliable parts extremely reliable.
Exactly.
And the researchers demonstrate that
And they demonstrate that
both of these processes occur when you fix the initial state of the Markov chain in a specific way.
In a very specific way.
Which is captured by the factorization of the period.
Right.
That's fascinating.
It is.
So what are the next steps in their proof?
They break down the proof into two parts, one for each type of polarization.
Got it.
For slow polarization,
Okay.
they utilize a series of lemmas, which are like mini theorems, to build a step-by-step argument for fast polarization.
They analyze a parameter called the Bhattacharyya parameter, which we discussed earlier.
Okay, before we delve into the specifics of those proofs, I think we should take a pause here.
All right.
This is a good stopping point.
Okay.
And I'm sure our listeners are eager to hear more about how they actually prove these concepts of slow polarization and fast polarization.
I agree. This is a good place to break.
Okay.
We've covered a lot of ground
in
understanding the foundation of their approach and the key elements of their proof strategy.
Sounds good.
Welcome back to our deep dive into constant weight polar codes.
Thanks.
Before we paused, we were discussing the paper's proof of Theorem 1, which guarantees the existence of these remarkable codes. We just started to explore the concepts of slow and fast polarization.
Yeah.
Are you ready to unpack how the researchers actually demonstrate these phenomena?
Absolutely. I'm particularly interested in how they approach the proof for slow polarization. Using those lemmas you mentioned. It seems like a very meticulous process.
You're right. It is quite meticulous.
Yeah.
They start with lemma 3. Which focuses on two random processes denoted by h hat and h. These processes essentially track the entropy values as our code undergoes the polarization process.
So if I understand correctly, H hat and H are like chronicles of the uncertainty in our message as it's encoded and decoded, right?
Yes.
We get to see how that uncertainty evolves over time.
Precisely. And lemma 3 proves that these processes converge, meaning they settle towards specific values as the sequence length increases. It's like observing a pendulum gradually coming to rest at its equilibrium point.
That's a good analogy.
Yeah.
But why is this convergence so important for their proof?
Well, this convergence is crucial because it allows us to analyze those final settled entropy values. Those values reveal a lot about the effectiveness of the polarization process. That's where lemma 8 comes in. It tells us that the limiting random variable for h hat, denoted by h hat infinity, can only be 0 or 1.
So in the long run, the uncertainty either completely vanishes or we're left with maximum uncertainty. There's no middle ground.
It's a fascinating consequence of polarization.
Yeah.
It pushes the entropy values to their extremes, which is precisely what we want for reliable communication. We either have complete certainty, which means we can perfectly decode the message, or we have complete uncertainty, which means those parts of the message are essentially useless for conveying information.
That makes sense.
Yeah.
But remember, we're dealing with periodic Markov chains here, right?
That's right.
Does that periodicity throw a wrench into the analysis?
You raise a valid point.
Yeah.
The periodicity could potentially complicate things. But the researchers address this in lemma 9. This lemma demonstrates that fixing the initial phase of the Markov chain doesn't affect the overall entropy rate.
So it doesn't matter where you start. on the cycle of the periodic process,
Yeah.
the average uncertainty over time remains the same.
Yes.
That simplifies things nicely.
Indeed it does.
Now, all these lemmas
Right.
build up to Proposition 10,
Exactly.
which formally establishes
Yeah.
the concept of slow polarization.
Yes.
Okay, time to connect the dots.
Okay.
What exactly does Proposition 10 tell us?
Proposition 10 states that as the sequence length grows,
Okay.
the proportion of indices with entropy less than a small value,
Okay.
which we can call n,
Right.
converges to a specific limit.
Okay.
This limit is 1 minus the conditional entropy rate,
Okay.
in simpler terms. Yeah.
We're identifying those parts of the message
Okay.
where the uncertainty is becoming very low.
So we're zeroing in
Look at
on
these things.
those reliable bits of information.
Yes.
The ones that are highly likely to be decoded correctly,
Right.
even in the presence of noise.
Yes.
And the proportion of these reliable bits is directly related to the entropy rate.
You've got it.
Okay.
It's like a mathematical guarantee
Right.
that we're successfully separating the signal from the noise.
That's pretty reassuring.
It is.
But Proposition 10 also tells us something about those indices with entropy greater than a 1 minus n, right?
Yes.
Those would be the unreliable parts of the message,
That's right.
the ones prone to errors.
You're absolutely right.
Yeah.
Proposition 10 also tells us that the proportion of those unreliable indices
Right.
converges to the conditional entropy rate itself.
Okay.
So as the polarization process unfolds, we're not only identifying the reliable bits.
But we're also pinpointing
Right.
those bits that are practically useless for conveying information.
It's like a two-pronged attack
Yeah.
on uncertainty.
Yes.
We're simultaneously identifying the good stuff and filtering out the noise.
That's right.
It's a very efficient process.
Indeed it is.
Now, we've thoroughly explored
Right.
the concept of slow polarization,
Yes.
but we haven't delved into fast polarization yet.
That's right.
This is where things get even more interesting,
Right.
wouldn't you say?
Absolutely. Fast polarization sounds like
What
where
else?
the real magic happens.
What can you tell me about it?
Fast polarization is all about
Okay.
how quickly those reliable bits become super reliable.
Okay.
And the key to understanding this process lies in analyzing something called the Bhattacharyya parameter,
Okay.
which we touched upon earlier.
All right. Remind me again.
Sure.
What exactly does the Bhattacharya parameter measure?
Think of it as a measure of similarity between two probability distributions.
Okay.
In our case, we're looking at the distributions of the received signal when I0 is sent versus when a 1 is sent.
Okay.
If the Bhattacharya parameter is low, it means those distributions are quite distinct, making it easier to distinguish between a 0 and a 1, which is precisely what we want for reliable decoding.
So a low Bhattacharya parameter implies high distinguishability,
Exactly.
leading to fewer errors.
Yes.
Conversely, a high Bhattacharya parameter means the distributions are very similar, making it difficult to tell which bit was actually sent.
Exactly. Now, how does this relate to fast polarization?
Right.
Well, lemma 12 provides that crucial link.
Okay.
It establishes a set of inequalities that connect the Bhattacharya parameter for consecutive steps in the polarization process.
So we're essentially analyzing how the distinguishability of our bits changes.
That's precisely it.
As they go through the encoding and decoding steps, right?
Yes.
We're tracking the evolution of that Bhattacharya parameter.
And the beauty of lemma 12 is that the inequalities it establishes demonstrate that the Bhattacharya parameter decreases exponentially fast for those reliable bits.
Exponentially fast. That sounds promising.
It is.
What are the implications of that?
It means that as the sequence length grows, those reliable bits become incredibly easy to distinguish from the noise, leading to exceptionally low error probabilities.
Wow.
It's like watching a snowball rolling down a hill. It starts small, but it rapidly gains momentum and size as it descends.
I'm starting to grasp the power of these codes.
Yeah.
But how do we know for sure that this fast polarization actually occurs?
That's a great question.
Is it just a theoretical possibility or is there concrete proof?
There's concrete proof, and it comes in the form of Proposition 14. This proposition builds on lemma 12 and utilizes a result from another paper known as Proposition 49 to formally prove that fast polarization does indeed occur.
Proposition 49 from another paper.
Yes.
It sounds like we're going deep down the rabbit hole of mathematics.
It can get a little deep.
Is it crucial that we understand
No, not.
the details of that external proposition?
What matters is that Proposition 14,
Okay.
leveraging this external result, guarantees the existence of a
Sure.
significant proportion of indices,
Okay.
where the Bhattacharyya parameter is incredibly small,
Right.
meaning those corresponding bits are super reliable.
Okay. So let me summarize what we've learned so far.
Right?
We have slow polarization,
Right.
which gradually identifies the reliable bits.
Yes.
And then fast polarization swoops in
Exactly.
and makes those reliable bits super reliable.
Yes.
It's a powerful combination.
It is.
But are we done with the proof of Theorem 1?
We're almost there.
Okay. What else is there?
We need one more ingredient, lemma 15.
Okay.
This lemma might seem a bit technical at first glance, as it deals with bounding probabilities and entropies when multiple events occur.
I remember that lemma involved some rather complex equations.
It can.
Can you give me the gist of it?
Sure.
Without getting too lost in the mathematical weeds.
Essentially, lemma 15 equips us with the tools to connect the overall behavior of our system to the behavior of individual events.
Okay.
It allows us to bridge the gap between the big picture and the fine-grained details.
So if I'm understanding correctly, we have slow polarization,
Right.
fast polarization, and this bridge building lemma 15.
Yes.
How do these elements finally come together to prove Theorem 1?
Remember that Theorem 1 guarantees the existence of these constant weight polar codes with a specific rate and vanishingly small error probability.
Right.
The proof elegantly weaves together all the elements we've discussed.
I'm all ears. Walk me through the final steps of their argument.
First, we utilize Proposition 14, which we know proves fast polarization to establish that there's a substantial proportion of bits with very low Bhattacharyya parameters under a specific event, denoted by this event captures the constraint that the initial state's phase modulo D is fixed.
Right. Remember our factorization of the period.
Exactly.
This is where it comes into play.
That's right.
So we have those highly reliable bits,
right,
but they're still operating under this broader event.
Yes.
We need to connect this back to
right,
our specific constraints
exactly,
on the initial and final states, right?
That's right.
The event hashtag from Theorem 1.
You're exactly right. And that's precisely where lemma 15 comes in.
Okay.
We use it to demonstrate that the Bhattacharyya parameters and entropies under our desired event, hashtag, are bounded by the corresponding values under scaled by a constant factor.
So even though hashtag is a more restrictive event,
right,
encompassing our specific constraints,
yes,
we can still relate its behavior
exactly
to the more general case of,
yes,
it's like saying,
right,
if it works for the broader scenario, it must also work for this specific case.
That's a great way to put it.
Okay.
And since we've already established that fast polarization occurs under this connection ensures that it also holds true under our specific constraints, hashtag.
That's a very elegant way
to complete the proof
by combining the results of slow polarization, fast polarization, and this clever bridging lemma. They've conclusively demonstrated the existence of these incredible constant weight polar codes.
Indeed, it's a testament to the power of rigorous mathematical analysis. They've carefully constructed a logical framework, piece by piece, to arrive at this remarkable result.
But wait, there's more, right?
Yes, there is.
The paper also has an appendix that delves into additional proofs.
Yes.
What can you tell me about those?
You're absolutely right.
Yeah.
The appendix contains proofs for lemmas 4 and 11, which provide further insights into the inner workings of these codes.
Before we dive into those, I think this would be a good place to pause again.
Okay.
We've covered a lot of ground.
We have.
And I'm sure our listeners would appreciate a moment
I agree.
to digest all this information.
It's always good to take a step back and reflect on the journey so far.
All right, let's jump back into this fascinating world of constant weight polar codes.
Right.
We were about to explore the appendix.
Yes.
Which I hear holds some hidden gems.
That's right.
In the form of proofs for lemmas 4 and 11.
Yes.
What can you tell me about lemma 4?
Lemma 4 focuses on establishing a minimum probability, a lower bound for the joint occurrence of three specific states in our Markov chain, as long as the sequence length is sufficiently large.
Why is this minimum probability so important?
It's vital because it guarantees a certain level of mixing within the Markov chain. Remember, we're dealing with periodic processes, which means they cycle through a specific set of states. This lemma ensures that we can reach any desired state with a reasonable probability, regardless of where we start in the cycle.
So lemma 4 acts like a safeguard.
Yeah, you could say that.
Preventing our code from getting stuck in a limited subset of states, right?
Yeah.
It ensures we have enough flexibility to generate the diverse sequences we need for reliable communication.
That's a great way to think about it. It's like ensuring all the ingredients in a cake batter are evenly distributed. So you don't end up with pockets of flour or sugar. You want that nice, consistent texture throughout.
I like that analogy. Now, the proof for lemma 4 seems to rely on a result from another paper.
Yes, it does.
Theorem 1.3, which deals with the properties of irreducible Markov chains. Do we need to dive into the details of that external theorem?
The key takeaway is that Theorem 1.3 provides the tools to establish this minimum probability. And the researchers cleverly apply those tools to our specific scenario involving these three states in our Markov chain.
Okay, so we don't need to go down that particular rabbit hole.
No.
What's interesting about this lemma is that it not only guarantees the existence of this minimum probability, but also provides a way to calculate it.
Exactly.
It's not just an abstract concept. It's a practical tool we can use.
Precisely. That's what makes this lemma so valuable. It bridges the gap between theoretical guarantees and practical applications.
All right. Let's move on to lemma 11, which I recall deals with bounding the probability of two dependent events occurring together. Can you refresh my memory on that one?
Certainly, lemma 11 states that under certain conditions, we can establish an upper bound on the probability of two events happening jointly. This upper bound is simply the product of their individual probabilities, scaled by a constant factor.
So even though the events are dependent, meaning the outcome of one influences the likelihood of the other.
Exactly.
We can still, for the purpose of this bound, treat them as if they were independent to some extent.
That's right. It's a bit counterintuitive, but that's the power of this lemma. It provides a way to simplify the analysis of dependent events by relating their joint probability to their individual probabilities. Of course, we need to account for that constant factor denoted by a pinna, which depends on the distribution of states in our Markov chain.
That constant factor captures the degree of dependence between the events. The proof for lemma 11 seems to heavily rely on the Markov property and the periodic structure of our process. Can you give me a high-level overview of how they use those properties?
They cleverly break down the events into smaller components, leveraging the Markov property to analyze the transitions between those components. The periodic structure allows them to establish relationships between probabilities at different points within a cycle of the Markov chain. By carefully piecing together these relationships, they arrive at the desired bound.
Now, I remember that lemma 11 played a crucial role in proving fast polarization.
It did.
Can you remind me how it fits into that bigger picture?
Remember lemma 12? Which established the inequalities connecting the Bhattacharyya parameters for consecutive steps in the polarization process. Well, lemma 11 is a key ingredient in proving those inequalities. It provides the tools to analyze the individual steps, which then allows us to demonstrate that the Bhattacharyya parameter decreases exponentially fast, leading to those highly reliable bits.
It's fascinating to see how all these pieces fit together.
It really is.
It's like a complex tapestry woven from individual threads of mathematical insight.
That's a great way to put it.
Each lemma plays its part
Right.
in contributing to the overall beauty and strength of the final result.
I can agree more.
We've covered an impressive amount of ground
We have.
in this deep dive.
Yeah.
We've explored the core concepts of constant weight polar codes.
Yes.
Delved into the intricate details
That's right.
of their mathematical proof.
Mm-hmm.
And even uncovered the hidden gems within those auxiliary proofs in the appendix.
It's been quite a journey.
What do you think are the most important takeaways?
I think one of the key takeaways is the remarkable power of these codes.
Right.
They provide a way to achieve reliable communication, even when faced with weight constraints, which are prevalent in various real-world applications. We've also seen how these codes are built upon a solid foundation of mathematical principles, with each lemma and proposition carefully grafted to ensure the validity and robustness of the final result.
I completely agree. This research is a beautiful example of how theoretical advancements can have significant practical implications.
Exactly.
It highlights the importance of rigorous mathematical analysis in pushing the boundaries of what's possible.
That's right.
In communication and data storage.
And what's truly inspiring is that this research opens up even more avenues for exploration. Given their success in achieving polarization for constant weight codes, it makes you wonder what other ties of constraints or conditions
what else
could be explored using this framework.
That's a great point. How might these findings influence the development of future communication and data storage technologies? Especially in areas where resource efficiency is critical.
That's a great question.
The possibilities seem endless.
Indeed, the possibilities are vast. I believe this research has the potential to significantly impact fields like data storage, wireless communication, and even cryptography.
Well, on that note of exciting possibilities, I think it's time to wrap up this deep dive.
Sounds good.
It's been a truly enlightening journey.
It has been.
And I want to thank you
You're welcome.
for expertly guiding us through the intricacies of this research.
It was all mine.
And to our listeners,
yes,
thank you for joining us.
Thanks for listening
on this intellectual adventure. We hope you found it as stimulating and insightful as we did.
It's been a pleasure.
If you're eager to delve deeper into the world of constant weight polar codes, we encourage you to explore the full research paper.
That's right.
It's a treasure trove of knowledge.
It is.
Waiting to be discovered.
And remember, the pursuit of knowledge is a never-ending journey.
It is.
Keep asking questions. Keep exploring. And keep pushing the boundaries of what,
Absolutely.
Until next time.
Sounds good. We're diving into some really cool research today, all about polar codes.
Oh, yeah.
But not just any polar codes. We're looking at a very specific type. Constant weight polar codes. They've got some really interesting applications, particularly in things like optical communications and data storage. The idea is you have this code where every single word has the same number of ones.
I see.
So that's what we're dealing with.
That's interesting.
It's kind of like a secret language with really strict rules.
Yeah, definitely. And what makes this deep dive even more exciting is the method that they use to actually generate these codes. Have you ever heard of periodic Markov chains?
I've encountered Markov chains. But to be honest, the periodic ones are a bit of a mystery to me. Could you maybe refresh my memory on those?
Absolutely. So think of a Markov chain as a system that kind of hops between different states. Kind of like if you had a frog jumping between lily pads. The key is that the probability of jumping to the next lily pad only depends on the lily pad it's currently on, not the path it took to get there.
Oh, so it's kind of like it only has a short-term memory.
Exactly.
Only remembering the present location.
Exactly. No.
Interesting.
Periodic Markov chains add a bit of a twist to this. They have this cyclical structure, meaning the frog would end up revisiting the same lily pads in a predictable pattern.
Interesting.
And it's this pattern that the paper uses to generate those constant weight codes.
That's fascinating. So the paper we're looking at today is constant weight polar codes through periodic Markov processes.
That's the one.
Okay.
And one of the key takeaways from the paper is this idea of polarization, which is this crucial process that makes these codes really efficient.
Right.
And this polarization happens when you use periodic Markov chains. But there's a catch.
Okay.
It only happens if you fix that starting state.
So it's like you're strategically placing the frog on a specific lily pad at the beginning.
You got it.
To make sure it hops in the pattern you want.
Exactly. By fixing that initial state, you ensure that all the code words generated by that Markov chain have the desired weight, which is that same number of ones.
Yeah, okay.
In this case.
Makes sense. Now, the paper actually provides a specific example to illustrate this.
Right.
In Figure 1.
Yeah, they give an example of a periodic Markov chain that generates these sequences with weight N2 for a sequence of length N.
Okay.
So in simpler terms, it basically creates sequences where exactly half the bits are ones.
So it's a clever illustration.
Right.
But the paper also points out that this specific chain, it only produces a subset of all possible weight N2 sequences.
Yeah, that's interesting because it kind of raises a question about whether we could expand that chain even further to unlock that full potential.
Right, we've opened the door, but we haven't stepped through it fully yet.
Exactly, there's more to discover.
Now, there's also Figure 2, which shows how this chain can actually be condensed to have fewer states while still generating the same set of sequences.
Exactly. It's all about optimizing the efficiency.
Right.
You simplify that generation process without sacrificing the quality of the codes.
Very elegant. Very nice.
Right.
Now, it's important to remember, though, that this example chain has some limitations.
Of course.
For example, if the sequence length isn't a multiple of the period, we need to constrain not just the initial state, but also the final state.
Right, like adding a finish line to make sure every runner completes that intended distance.
I like that analogy.
Yeah.
And the paper doesn't actually limit itself to just weight N2.
No, it doesn't.
It demonstrates how we can construct similar chains to generate sequences with weights falling within specific ranges.
Right, so it's not limited to a single weight, but more like a range of weights. Which definitely broadens the applicability.
This is where things get a little bit more abstract. The paper delves into the mathematical heart of the matter with Theorem 1. And Theorem 1 rigorously proves that polarization happens when you fix the initial state of a periodic Markov chain.
It's like having that mathematical blueprint.
Right.
Yeah.
That guarantees the code's performance.
It forms the foundation for building a practical coding scheme.
So let's take a closer look at Theorem 1.
Okay.
What does it state exactly?
All right, so Theorem 1 states that for any irreducible and a periodic Markov chain, the polar transform applied to the chain with a fixed initial state exhibits polarization.
Okay, that's a bit to unpack.
Yeah.
Can you maybe elaborate on what irreducible and a periodic mean?
Sure. So an irreducible Markov chain basically means that it's possible to get from any state to any other state in a finite number of steps. So it's like a connected network. Right, where you can always find a path between any 2 points.
I see.
And a periodic basically means that the chain doesn't get stuck in a repeating cycle of states.
Okay, so these properties are essential
Yeah.
for ensuring that the polarization process can actually unfold as expected.
Precisely. And the paper provides a detailed proof of this theorem,
Okay.
walking us through all the steps involved in demonstrating polarization.
Now, before we dive into the proof,
Sure.
I'd like to touch upon a point you mentioned earlier
Okay.
about partitioning the states of our Markov chain into different phases.
Right.
Could you explain that concept a bit further?
Yeah. So the idea of partitioning states into phases comes from that periodic nature of our Markov chain. Remember, a periodic Markov chain, it revisits states in this cyclical pattern.
Yeah.
We can divide the cycle into segments or phases based on the structure of that chain.
So each phase represents a specific portion of the chain's cyclical journey.
Exactly. And the proof of Theorem 1 cleverly focuses on fixing the phase of that initial state.
Okay.
This means we're starting our journey at a specific point within that periodic cycle.
That makes sense.
Right.
So by fixing the phase,
Yeah.
we're essentially setting the stage
Exactly.
for the polarization process to unfold in a controlled manner.
Precisely. And to demonstrate this, the paper walks us through two distinct approaches. Slow polarization and fast polarization.
Okay, I'm particularly intrigued by the concept of fast polarization.
Yeah, fast polarization is crucial for building codes that operate efficiently in the real world.
Okay.
It refers to the rate at which that polarization process actually occurs.
Mm.
So in fast polarization, the Bhattacharyya parameters,
Uh-huh.
which measure the distance between the probability distributions of code word bits,
Right.
they converge exponentially fast
Okay.
as we apply more and more of those polar transformations.
So it's like the code words are quickly sorting themselves into those that are destined for perfect predictability and those destined for perfect unpredictability.
Exactly. And fast polarization allows us to achieve those theoretical limits of data transmission,
Okay.
but in a practical time frame.
That's impressive.
Yeah.
Now, I understand that the proof relies on some pretty heavy-duty mathematical tools,
Of course.
things like entropy,
Right.
Bhattacharya parameters,
Yeah.
and total variation.
Uh-huh.
Could you maybe provide some insights into how those concepts are used?
Sure. So entropy in this context is a measure of the uncertainty or randomness of a random variable.
Yeah.
So the higher the entropy, the more unpredictable that variable is.
Okay.
Bhattacharya parameters and total variation.
Right.
They're actually measures of the distance or similarity
Uh-huh.
between two probability distributions.
So entropy kind of helps us quantify that surprise factor
That's a great way to put it.
of a random variable.
Yeah.
And then the other two
Mm-hmm.
tell us how close or far apart
Exactly.
two probability distributions are.
Exactly. And the researchers cleverly manipulate these parameters to demonstrate both slow and fast polarization.
I'm eager to delve into the actual proofs
Okay.
of slow and fast polarization.
Right.
Where do we begin?
Well, the proofs are pretty intricate,
Okay.
but let's start with slow polarization.
Right.
The paper first introduces a key concept: the factorization of the Markov chain's period.
All right.
Remember, the period of a periodic Markov chain is the number of steps it takes to return to the same state.
Right. So it's like the length of one complete cycle of
Yeah.
our frog's journey.
Splicely.
Right.
And the paper expresses this period as P equal dq,
Okay.
where d is a power of 2,
Mhm.
and a q is an odd number.
Interesting.
And this factorization plays a crucial role in the proof.
It seems like such a small detail,
Right.
but I have a feeling it's a lot more significant
You're absolutely right.
than it appears.
This factorization allows the researchers to exploit that cyclical structure of the Markov chain and leverage the properties of powers of 2 and odd numbers in their proof.
I'm intrigued.
Yeah.
How does this factorization actually come into play
Okay.
in the proof of slow polarization?
So the proof of slow polarization is structured as a series of lemmas
Okay.
that build upon each other,
Mm-hmm.
each one establishing a key property of that polarization process.
It's like constructing a building brick by brick.
Exactly. And each lemma uses the factorization of that period
Yeah. Okay.
in a clever way to demonstrate how the entropy of specific code word bits evolves as we apply more and more polar transformations.
Okay, so let's take a look at the first lemma in this chain.
All right.
Lemma 3.
So lemma 3 focuses on the convergence of certain random processes related to the entropy of our code word bits.
Okay.
It establishes that as we apply more and more polar transformations, these processes steadily approach these well-defined limits.
So it's like saying that the entropy of certain code word bits settles down into
Exactly.
a predictable pattern
Precisely.
as we keep applying the polar transform.
And these limits are actually represented by random variables that capture that long-term behavior of the entropy as our code words become increasingly polarized.
Okay, and how is that factorization of the period
Right.
used in proving lemma 3?
So the proof of lemma 3 relies on this concept of bounded martingales.
Martingales.
Yeah.
I've encountered that term before in probability theory.
Right.
Could you refresh my memory on what they represent?
Sure. Imagine you're playing a fair coin toss game.
Okay.
In each round, you bet a certain amount,
Uh-huh.
and you either win or lose based on the outcome of that coin toss.
Right.
Your expected winnings after each round, given all the information up to that point,
Okay.
is equal to your current winnings.
Yeah.
That's the essence of a martingale.
So it's like a game
Yeah.
where your past performance doesn't influence your expected future games.
Exactly. Now, in the context of our proof, these martingales help us analyze how the entropy of our code word bits evolves. As we apply those polar transformations, they provide a powerful framework for understanding that long-term behavior.
And the boundedness of the martingales is ensured
You got it.
by the factorization of the period.
Exactly. The factorization, particularly the presence of that power of 2 term, ensures that the martingales that we're dealing with are bounded,
Okay.
which is crucial for proving convergence.
Fascinating.
Yeah.
So lemma 3 establishes this fundamental property
Right.
of the polarization process, that convergence of entropy towards well-defined limits.
Precisely.
What about the subsequent lemmas?
Okay.
How do they contribute to the overall proof of slow polarization?
Well, the subsequent lemmas, they build upon that foundation laid by lemma 3.
Okay.
Each one adding another piece to the puzzle of slow polarization.
So it's like a relay race,
Exactly.
where each runner carries the baton a bit further towards the finish line.
Exactly. So lemma 4, for instance, establishes a lower bound on certain probabilities within our Markov chain. It ensures that certain transitions between states have a non-zero probability of occurring.
So we don't want our Markov chain
Right.
to get trapped in a dead end,
Exactly.
unable to explore all the necessary states.
Precisely. And the proof of lemma 4 leverages the fact that our Markov chain is irreducible,
Well,
meaning we can eventually reach any state from any other state.
it's like having a well-connected transportation system
Exactly.
where you can always find a route
You got it.
between any two destinations.
Now, lemma 5
Okay.
delves a little deeper into the relationship between different entropy terms
Okay.
that arise during that polarization process.
So we're analyzing how that surprise factor of different code word bits changes
You got it.
as we apply the polar transform.
Exactly. And lemma 5 establishes these inequalities between these entropy terms,
Okay.
paving the way for proving that polarization indeed takes place.
And I imagine the factorization of the period plays a role here as well.
It does. That specific structure of our periodic Markov chain, with its cyclical pattern of phases,
Okay.
is crucial for establishing these inequalities.
Right.
The factorization of the period helps us relate those entropy terms at different stages of the polarization process.
This is where those intricate details of the Markov chain structure really come into play.
Absolutely. And then we have lemma 6,
Okay.
which is a pivotal point in the proof of slow polarization.
Okay.
This lemma identifies these special triplets of states.
Triplets of states.
Yeah.
Why triplets?
So the choice of triplets is carefully orchestrated to leverage that cyclical nature of our Markov chain
Okay.
and the properties of the factorization PE equals DQ. These triplets, denoted as B0, B sharp, B2 sharp,
Right.
are chosen such that their phases have this specific relationship
Okay.
dictated by the factorization.
So we're strategically selecting states
Precisely.
based on their position
Yeah.
within the Markov chain cycle.
Exactly. And the proof of lemma 6 actually involves some techniques from number theory.
Number theory.
Including the Chinese remainder theorem
Okay.
and Euler's theorem.
Wow. It's impressive how this proof draws upon tools
I know, right?
from different branches of mathematics.
It highlights that interconnected nature of mathematical concepts. And these number theory tools allow us to prove that these triplets of states,
Right.
satisfying the desired conditions, always exist
Okay.
within our periodic Markov chain.
Yeah, that's quite a feat.
It is.
Now, once we have these special triplets,
Right.
how do we proceed with the proof of slow polarization?
That's where corollary 7 comes in.
Okay.
It follows directly from the previous lemmas and establishes a lower bound on the difference between certain entropy terms.
So it's like quantifying the progress of polarization,
Exactly.
showing that the entropy of certain code word bits is indeed moving towards either 0 or 1.
Precisely. Corollary 7 provides that concrete measure of the polarization process.
Okay.
Showing that it's not just a theoretical concept, but something we can observe in the behavior of our entropy terms.
And this progress is guaranteed by the properties established in the previous lemmas.
Exactly, including the existence of those special triplets of states.
Right.
Now we come to lemma 8,
Okay.
which focuses on that limiting random variable we introduced earlier, denoted as AF.
And if I recall correctly, this random variable captures the long-term behavior of the entropy
Yes.
of certain code word bits as we apply more and more polar transformations.
You got it. And lemma 8 asserts that this limiting random variable can only take on the values of 0 or 1
Okay.
with probability 1.
So it's like saying that each bit in our code word eventually settles into a state
Exactly.
of either complete certainty or complete uncertainty.
Exactly. And this is a crucial step towards achieving error-free communication, because it means we can reliably distinguish between those highly predictable bits and those highly unpredictable bits.
Makes sense.
Right.
And how does the proof of lemma 8 leverage the previous results?
So the proof uses a proof by contradiction, assuming that there's a non-zero probability that that limiting random variable lies between 0 and 1.
Okay.
By carefully analyzing the implications of this assumption,
Uh-huh.
the proof arrives at a contradiction,
Right.
forcing us to conclude that the random variable must indeed be either 0 or 1.
Proof by contradiction, a classic
Right.
and powerful technique.
Indeed.
Okay, so to connect this back to the concept of entropy rate,
Okay.
the paper introduces lemma 9,
Right.
which examines the impact of fixing the initial phase
Uh-huh.
of our Markov chain.
Right. So the entropy rate, if you remember, represents that average amount of information contained in each bit of our code word
Okay.
as the sequence length grows infinitely long.
Right, that's the entropy rate.
Exactly. And lemma 9 elegantly demonstrates that the entropy rate remains invariant,
Okay.
even if we constrain our Markov chain to start at a specific point within its periodic cycle.
So we're not sacrificing any information capacity
Yeah.
by fixing the initial phase.
Lemma 9 assures us that we can impose this constraint without affecting the overall information content
Okay.
of our code words. And the proof cleverly manipulates conditional entropy terms, exploiting that Markov property and the stationarity of our process.
Stationarity.
Yes.
Do you elaborate on that concept?
Yeah, stationarity in this context basically means that the statistical properties of our Markov chain don't change over time.
Sure.
It's kind of a river with a constant flow rate.
Okay.
The amount of water passing a certain point remains the same over time.
I see. So the stationarity of our Markov chain
Right.
simplifies the analysis because we don't have to deal with time-varying properties.
Precisely. And finally, we arrive at proposition 10,
Okay.
the culmination of our exploration of slow polarization. This proposition brings together all the previous lemmas
Right.
to provide a precise mathematical description of how the entropy of our code word bits evolves as we apply more and more polar transformations.
So it's like the grand finale
Yeah.
of our slow polarization symphony,
That's a great analogy.
bringing all the instruments together
Right.
to create a harmonious conclusion.
So Proposition 10 establishes the convergence of specific entropy terms, demonstrating that as we apply more and more polar transformations, the entropy of certain code word bits approaches either 0 or 1,
Right.
depending on the corresponding limiting random variable.
It's like watching our code word bits gradually segregate
Exactly.
into two distinct camps.
Uh-huh.
Those destined for perfect predictability
Right.
and those destined for perfect unpredictability.
And this segregation is the essence of polarization, the key to achieving that reliable communication.
This has been an incredibly illuminating journey
It has.
through the intricacies of slow polarization.
Yeah.
Now I'm eager to turn our attention to fast polarization
Okay.
and explore how the paper tackles that aspect of the proof.
All right, fast polarization is where things get even more interesting.
Okay.
The paper introduces a new set of tools and definitions.
To demonstrate how that polarization process can occur exponentially fast.
Okay.
Are you ready to delve into that?
I'm ready.
Yeah, fast polarization really showcases the efficiency of this coding scheme,
Okay.
while slow polarization focuses on that eventual convergence of entropy. Fast polarization delves into how quickly that convergence happens. It uses a different set of tools,
Okay.
building on what we learned with slow polarization.
So instead of just knowing the code words will eventually become predictable or unpredictable,
Right.
we're now looking at how fast they get there.
Exactly. And to do this, the paper uses a tool you're probably familiar with,
Okay.
the Bhattacharyya parameter.
Uh-huh.
It measures how similar or distant the probability distributions of two random variables are.
I remember we talked about that briefly before. It's
Yeah.
like determining how much two probability distributions overlap.
Precisely. A Potcast parameter close to 0
Okay.
means the distributions are almost identical,
Uh,
suggesting high predictability.
A value close to 1 means they're very different, implying high unpredictability.
So in fast polarization, we're interested in how quickly these Potcast parameters move towards 0 or 1.
That's the heart of it as we
Okay.
apply the polar transform.
Okay.
And the paper shows this beautifully. It introduces lemma 11,
Okay.
which provides a way to bound the probability of two dependent events occurring.
Dependent events.
Yeah,
So events where the outcome of one influences the other?
exactly. It's like flipping a coin,
Okay.
where the probability of getting heads on the second flip
Right.
depends on whether you got heads or tails on the first.
I see.
Right.
Okay.
And how does this lemma help us understand fast polarization.
Yeah. How does that tie in?
Well, it allows us to relate the joint probability of those dependent events to their individual probabilities.
Okay.
And this connection is crucial for analyzing how the Bhattacharya parameters evolved.
It's like understanding the domino effect.
Right.
How one event triggers a chain reaction.
Great analogy.
Yeah.
Now, lemma 12
Okay.
is where the Bhattacharya parameters truly take center stage.
Okay.
This lemma establishes inequalities that relate the Bhattacharya parameters of certain code word bits at different stages of that polarization process.
So we're tracking how that similarity or distance between the probability distributions of code word bits changes as we repeatedly apply the polar transform.
Precisely. And these inequalities show that the Bhattacharya parameters exhibit that same behavior that we saw with the entropy in slow polarization.
Okay.
They either converge to 0, indicating high similarity, or to 1, indicating high dissimilarity.
It's like watching the probability distributions of our code word bits.
Yeah.
Either merging together or drifting far apart.
Exactly.
As we apply more and more polar transformations.
Exactly. But here's where the concept of fast comes in.
Okay.
Lemma 12 shows that this convergence happens exponentially fast.
So instead of a gradual drift, it's more like a rapid acceleration.
Precise.
Towards either similarity or dissimilarity.
You got it. And to prove these inequalities, the paper cleverly manipulates conditional probability terms.
Okay.
Leveraging the structure of our periodic Markov chain and the conditioning on that initial phase.
That initial phase seems to be a recurring theme.
Yeah.
Throughout these proofs.
Yeah.
It's like a guiding principle.
It is.
For ensuring polarization happens as expected.
You're absolutely right. The choice of the initial phase sets the stage for the entire polarization process. Now, lemma 13 introduces a new set of parameters denoted with the symbol that are closely related to the Bhattacharya parameters.
So it's like viewing the same concept of probability distribution closeness through a slightly different lens.
That's a great way to put it.
Yeah.
These parameters capture similar notions of similarity or dissimilarity, but they use total variation distance
instead of Bhattacharya distance.
And how does this new perspective help us understand fast polarization?
Well, lemma 13 establishes inequalities for these Abikar parameters that are analogous to those for the Bhattacharya parameters. This shows that these new parameters also exhibit that crucial property of converging rapidly to either 0 or 1.
It's like having two witnesses confirming the same event,
right?
Adding more weight to the evidence.
Exactly. The paper provides multiple perspectives on the same phenomenon, reinforcing the robustness of that polarization process.
Okay. And with all these pieces in place, we arrive at Proposition 14, which seems to be the crowning achievement of the fast polarization proof.
It is.
What does this proposition tell us?
So Proposition 14 brings everything together beautifully.
Okay.
It establishes that fast polarization phenomenon for the case where we condition on that initial phase of our Markov chain. It shows that the fraction of code word bits with Bhattacharya parameters close to 0
approaches the entropy rate.
So the proportion of highly predictable bits aligns with the entropy rate.
Yes, and simultaneously, the fraction of code word bits with Bhattacharya parameters close to 1 approaches 1 minus the entropy weight.
So the proportion of highly unpredictable bits also falls into place as expected.
Exactly. It's like watching the code words rapidly sorting themselves into their destined categories.
Yeah.
And the beauty of this result is that it's proven for the general case of any irreducible and a periodic Markov chain.
Right.
Not just specific examples.
This is quite a powerful result.
It is.
But how does the paper bridge the gap between Proposition 14, which focuses on conditioning on the initial phase, and Theorem 1, which requires conditioning on the specific starting and ending states?
Excellent question. That's where lemma 15 comes into play.
Okay.
It provides a set of inequalities that allows us to relate Bhattacharya parameters and OS parameters under these different conditioning scenarios.
So it's like building a bridge.
You got it.
Between the results obtained for a broader set of conditions to the more specific conditions required for Theorem 1.
That's a perfect analogy. Lemma 15 is that crucial link that allows us to leverage the power of Proposition 14 to prove that more general result of Theorem 1.
It's fascinating how each lemma builds upon the previous ones,
It is.
creating this chain of logic
Right.
that leads us to the final proof.
Indeed. And to prove Lemma 15, the paper relies on some fundamental mathematical tools,
Okay.
including the Cauchy-Schwarz inequality and the triangle inequality.
Right.
It's a beautiful example of how classic mathematical principles can be used to prove sophisticated results.
It's a testament to the power of those fundamental mathematical tools.
Absolutely.
Now, with Lemma 15 in hand,
Right.
we're finally equipped to tackle the ultimate goal,
Yeah.
proving Theorem 1.
The proof of Theorem 1 is a masterful synthesis. Of all the concepts that we've explored so far,
Okay.
it begins by recalling the factorization of that Markov chains period, that familiar expression EP equire DQ.
Right.
It then applies proposition 14, but with a clever substitution.
Okay.
Instead of using V directly, it uses E plus 12, 2.
It seems like we're fine-tuning the parameters from proposition 14 to align with the specific conditions required for Theorem 1.
Yeah, exactly.
Why this particular substitution?
Well, this substitution helps bridge that gap between the conditions in proposition 14, which involve conditioning on the initial phase, and the conditions in Theorem 1, which require conditioning on both the initial and final states.
So it's like adjusting the lens
Exactly.
to bring the picture into sharper film.
You got it. And the key insight is to demonstrate that there's a constant factor B, independent of the sequence length and the specific bit position, that allows us to relate the Bhattacharyya parameters. Right.
Under those different conditioning scenarios, this constant factor B acts like a scaling factor, enabling us to translate those results from proposition 14 to the context of Theorem 1.
It's like finding the missing piece of the puzzle that connects everything together.
Precisely. And to find this crucial constant B,
the
proof cleverly utilizes Lemma 4, which, if you recall, establishes a lower bound on certain probabilities within our Markov chain.
It's amazing how seemingly disparate pieces of the proof come together to form a cohesive whole.
It's a testament to the elegance and interconnectedness of mathematics. The proof then continues by meticulously applying Lemma 15 to relate the Potcharya parameters and the bed parameters under those different conditioning scenarios.
So we're carefully aligning all the pieces, ensuring they fit together perfectly to reveal that grand picture of Theorem 1.
Exactly, and with all the pieces in place. The proof concludes by demonstrating that the limits established for the Bhattacharya parameters in proposition 14 hold true under those more specific conditions of Theorem 1.
So we've essentially shown that regardless of whether we condition on the initial phase or the specific initial and final states, the polarization phenomenon still holds.
Exactly.
And it happens fast.
Precisely, that's the power of Theorem 1. It establishes that solid mathematical foundation for the remarkable properties of constant weight polar codes generated using those periodic Markov chains.
This has been an incredible journey.
It has been.
We've gone from the basic idea of Markov chains to the intricacies of slow and fast polarization, and finally to the grand finale of proving Theorem 1. It's truly remarkable how all these concepts interweave.
It is.
To create a beautiful tapestry of mathematical insight.
It's a testament to the power of human ingenuity and the elegance of mathematical reasoning.
And this is just the beginning. This paper opens up exciting avenues for future research, particularly in exploring those practical applications of these codes in real-world communication systems.
Indeed, the world of constant weight polar codes is brimming with potential.
It is.
I'm grateful for this deep dive.
Well, the pleasure was all mine.
It's been an enlightening experience.
Remember, the pursuit of knowledge is a continuous journey. And each new discovery brings us closer to unlocking the mysteries of the universe.
I'm ready to explore fast polarization.
All right, so fast polarization really showcases the efficiency of this coding scheme. While slow polarization focuses on that eventual convergence of entropy, fast polarization delves into how quickly that convergence happens. It uses a different set of tools, building on what we learned with slow polarization.
So instead of just knowing the code words will eventually become predictable or unpredictable, we're now looking at how fast they get there.
Exactly. And to do this, The paper uses a tool you're probably familiar with,
Okay.
the Bhattacharyya parameter.
Uh-huh.
It measures how similar or distant the probability distributions of two random variables are.
I remember we talked about that briefly before.
Yeah.
It's like determining how much two probability distributions overlap.
Precisely, a Bhattacharya parameter close to 0
Okay.
means the distributions are almost identical, suggesting high predictability.
But
A value close to 1 means they're very different, implying high unpredictability.
so in fast polarization, we're interested in how quickly these Bhattacharya parameters move towards 0 or 1.
That's the heart of it,
Right.
as we apply the polar transform.
Okay.
And the paper shows this beautifully. It introduces lemma 11,
Yep.
which provides a way to bound the probability of two dependent events occurring.
Dependent events.
Yeah.
So events where the outcome of one influences the other.
Exactly. It's like flipping a coin,
Okay.
where the probability of getting heads on the second flip.
Right. It depends on whether you got heads or tails on the first.
I see.
Right.
Okay.
And how does this lemma help us understand fast polarization?
Yeah, how does that tie in?
Well, it allows us to relate the joint probability of those dependent events to their individual probabilities.
Okay.
And this connection is crucial for analyzing how the Potcharya parameters evolve.
It's like understanding the domino effect, how one event triggers a chain reaction.
Great analogy.
Yeah.
Now, lemma 12
Okay.
is where the Potcharya parameters truly take center stage.
Okay.
This lemma establishes inequalities that relate the Potcharya parameters of certain code word bits at different stages of that polarization process.
So we're tracking how that similarity or distance
Right?
between the probability distributions of code word bits changes
Yeah.
as we repeatedly apply the polar transform.
Precisely. And these inequalities show that the Potcharya parameters exhibit that same behavior that we saw with the entropy in slow polarization.
They either converge to 0, indicating high similarity, or to 1 free, indicating high dissimilarity.
It's like watching the probability distributions of those code word bits,
Yeah,
either merging together or drifting far apart
exactly.
as we apply more and more polar transformations.
Exactly. But here's where the concept of fast comes in.
Okay.
Lemma 12 shows that this convergence happens exponentially fast.
So instead of a gradual drift,
Right.
it's more like a rapid acceleration
Precisely.
towards either similarity or dissimilarity.
You got it. And to prove these inequalities, the paper cleverly manipulates conditional probability terms,
Okay.
leveraging the structure of our periodic Markov chain and the conditioning on that initial phase.
That initial phase seems to be a recurring theme
Yeah, it is.
throughout these proofs.
Yeah.
It's like a guiding principle for ensuring polarization happens as expected.
You're absolutely right. The choice of the initial phase sets the stage for the entire polarization process. Now, lemma 13
Okay.
introduces a new set of parameters
Okay.
denoted with the symbol
Okay.
that are closely related to the Bhattacharya parameters.
Well, it's like viewing the same concept of probability distribution closeness
Right.
through a slightly different lens.
That's a great way to put it.
Yeah.
These parameters capture similar notions of similarity or dissimilarity,
Okay.
but they use total variation distance
Uh-huh.
instead of Bhattacharya distance.
And how does this new perspective help us understand fast polarization?
Well, lemma 13 establishes inequalities for these parameters
Okay.
that are analogous to those for the Bhattacharya parameters. This shows that these new parameters also exhibit that crucial property of converging rapidly to either 0 or 1.
It's like having two witnesses confirming the same event,
Right.
adding more weight to the evidence.
Exactly. The paper provides multiple perspectives on the same phenomenon, reinforcing the robustness of that polarization process.
Okay, and with all these pieces in place,
Right.
we arrive at Proposition 14,
Yes.
which seems to be the crowning achievement of the fast polarization proof.
It is.
What does this proposition tell us?
So Proposition 14 brings everything together beautifully.
Okay.
It establishes that fast polarization phenomenon for the case where we condition on that initial phase of our Markov chain. It shows that the fraction of code word bits with Bhattacharya parameters close to 0 approaches the entropy rate.
So the proportion of highly predictable bits
Right.
aligns with the entropy rate.
Yes. And simultaneously, the fraction of code word bits with Bhattacharya parameters close to 1 approaches 1 minus the entropy rate.
So the proportion of highly unpredictable bits also falls into place as expected.
Exactly. It's like watching the code words rapidly sorting themselves
Right.
into their destined categories.
Yeah.
And the beauty of this result is that it's proven for the general case of any irreducible and a periodic Markov chain.
Right.
Not just specific examples.
This is quite a powerful result.
It is.
But how does the paper bridge the gap between proposition 14, which focuses on conditioning on the initial phase,
right,
and theorem 1, which requires conditioning on the specific starting and ending states?
Excellent question. That's where lemma 15 comes into play.
Okay.
It provides a set of inequalities that allows us to relate Bhattacharya parameters and I's parameters under these different conditioning scenarios.
So it's like building a bridge.
You got it.
Between the results obtained for a broader set of conditions to the more specific conditions required for theorem 1.
That's a perfect analogy. Lemma 15 is that crucial link that allows us to leverage the power of proposition 14 to prove that more general result of theorem 1.
It's fascinating how each lemma builds upon the previous ones.
It is.
Creating this chain of logic that leads us to the final proof.
Indeed. And to prove lemma 15, the paper relies on some fundamental mathematical tools, including the Cauchy-Schwarz inequality and the triangle inequality. It's a beautiful example of how classic mathematical principles can be used to prove sophisticated results.
It's a testament to the power of those fundamental mathematical tools.
Absolutely.
Now with lemma 15 in hand, we're finally equipped to tackle the ultimate goal, proving theorem 1.
The proof of theorem 1 is a masterful synthesis of all the concepts that we've explored so far. It begins by recalling the factorization of that Markov chains period, that familiar expression PEDQ. It then applies proposition 14, but with a clever substitution. Instead of using V directly, it uses V plus 12 too.
It seems like we're fine-tuning the parameters from proposition 14 to align with the specific conditions required for theorem 1.
Exactly.
Why this particular substitution?
Well, this substitution helps bridge that gap between the conditions in proposition 14, which involve conditioning on the initial phase, and the conditions in theorem 1, which require conditioning on both the initial and final states.
So it's like adjusting the lens to bring the picture into sharper focus.
You got it. And the key insight is to demonstrate that there's a constant factor B, independent of the sequence length and the specific bit position, that allows us to relate the Bhattacharya parameters under those different conditioning scenarios. This constant factor B acts like a scaling factor, enabling us to translate those results from proposition 14 to the context of theorem 1.
It's like finding the missing piece of the puzzle that connects everything together.
Precisely. And to find this crucial constant B,
the
proof cleverly utilizes lemma 4, which, if you recall, establishes a lower bound on certain probabilities within our Markov chain.
It's amazing how seemingly disparate pieces of the proof come together to form a cohesive whole.
It's a testament to the elegance and interconnectedness of mathematics. The proof then continues by meticulously applying lemma 15 to relate the Bhattacharya parameters and the S parameters under those different conditioning scenarios.
So we're carefully aligning all the pieces.
Precise.
Ensuring they fit together perfectly. To reveal that grand picture of theorem 1.
Exactly. And with all the pieces in place, the proof concludes by demonstrating that the limits established for the Bhattacharya parameters in proposition 14 hold true under those more specific conditions of theorem 1.
So we've essentially shown that regardless of whether we condition on the initial phase or the specific initial and final states, the polarization phenomenon still holds.
Exactly.
And it happens fast.
Precisely. That's the power of theorem 1. It establishes that solid mathematical foundation
for the remarkable properties of constant weight polar codes generated using those periodic Markov chains.
This has been an incredible journey.
It has been.
We've gone from the basic idea of Markov chains to the intricacies of slow and fast polarization, and finally to the grand finale of proving theorem 1. It's truly remarkable how all these concepts interweave
It is.
to create a beautiful tapestry of mathematical insight.
It's a testament to the power of human ingenuity
Yeah.
and the elegance of mathematical reasoning.
Mm.
And this is just the beginning.
Okay.
This paper opens up exciting avenues for future research,
Right.
particularly in exploring those practical applications of these codes in real-world communication systems.
Indeed, the world of constant weight polar codes is brimming with potential.
It is.
I'm grateful for this deep dive.
Well, the pleasure was all mine.
It's been an enlightening experience.
Remember, the pursuit of knowledge is a continuous journey.
And each new discovery brings us closer to unlocking the mysteries of the universe.
All right, so today we're diving deep into constant weight polar codes. They're these error-correcting codes. And, well, the way they're made in this paper we're looking at today is kind of wild.
Yeah, pretty unexpected.
Yeah. Constant weight polar codes through periodic Markov processes.
He uses Markov chains, not really where I would have gone first.
Right, especially since, haven't we kind of already ruled those out?
Well, we knew periodic Markov chains weren't supposed to work with polar codes, but this paper shows how to make it happen.
Okay, so before we get into all that, can we just, for anyone who's maybe a little rusty, what are constant weight codes in the first place?
Basically, every code word has the exact same number of 1 bits.
Okay, so that's like a restriction.
It is, but it's a good thing for some applications.
Oh, I see. Like it makes them better suited for certain things.
Exactly. Things like optical communication or DNA storage or flash memories.
Interesting. Okay, so where do the Markov chains come in? I always think of those as like predicting what happens next in a sequence.
Right, but here we're using them to actually generate those constant weight codes. It's a special type, though, a periodic Markov chain. Each state in the chain is a specific weight, and moving between them is like adding a 0 or 1 to the sequence.
So you're basically building the code word as you move through the chain.
Exactly.
Okay, cool. Now, the paper makes a big deal about this whole fixing the initial state thing. Why is that so important?
It's kind of the key to the whole thing. That initial state guarantees we start from a specific weight, so no matter what path we take through the chain, we always end up with a code word that has that constant weight we're looking for.
Otherwise, it'd just be random, huh?
Exactly. We'd have no control over the final weight.
Gotcha. So it's like setting the starting point on a map. Okay, now I know the paper uses a lot of figures. Can we just take a quick look at figure 1?
Sure. It shows a chain that generates codes where the weight is half the total length of the sequence.
Okay, and each of those little circles is a different state, right?
Right. And the arrows show how we can transition between them.
Okay, and I see it says P = 4. What's that all about?
That's the period of the chain. It means there are 4 phases before the pattern repeats.
So how does that relate to the constant weight being half the length?
Well, the period is always twice the weight we want. So in this example where we want the weight to be half the sequence length, the period is 4.
Gotcha. Okay, so what about that starting point, the Y?
That's our initial state. It's what makes sure every sequence we generate will have the right weight. You can follow the arrows, and no matter which path you take, you always end up at the bottom level, which represents a sequence with that desired weight.
Clever. And what are those numbers next to the arrows?
Oh, those are the probabilities of taking each transition.
Okay, so they're not all the same.
Not in this case, no. We want all the valid sequences to be equally likely, and there are 6 of them.
Oh, right. Because there are 6 different ways to have 2 1 bits out of 4 total bits, combinatorics. Okay, so that makes sense. Now, figure 2 looks kind of similar, but simpler.
It is. Figure 2 is basically a more compact version of the same chain in figure 1. It just combines states that share the same phase and weight.
So it's like a simplified view, but still gives all the same info.
Exactly.
Cool. Now, can we always get that exact half and half weight? What if we need something else?
Well, the paper actually shows how to generalize this. You can create sequences with weights like USHAG or USHAG, where U is any rational number between 0 and 1.
Hold on. What are those symbols again?
Oh, those are just floor and ceiling functions. They
Yeah.
mean you round down or up to the nearest integer.
Okay, got it. So we're not just stuck with half.
Nope, we can get a whole range of weights.
So how do you make that happen?
It comes down to choosing the right period and starting state. You can fine-tune things to get the way you need.
Wow, so we've got options. What about figure 3, though? That one looks totally different.
Yeah, that's in a periodic chain.
Meaning what, it doesn't repeat?
Right, and it's used to create sequences where the weight modulo 1 is fixed.
Okay, now you've lost me. Weight modulo 1.
Basically, instead of looking at the exact weight, you look at the remainder after you divide by 1.
So like the fractional part.
Yeah, exactly.
And why would we care about that?
Well, it's useful in some systems where you want to avoid certain patterns, like too many 1 bits in a row.
Oh, I see. You're controlling the structure of the code word in a different way.
Exactly.
Clever. So how does this periodic chain make that happen?
It's all about fixing both the initial A and D final states to be 0. The way the transitions are set up, it guarantees those sequences will have the right modulo weight.
Okay, cool. So we've looked at these chains, and they're designed to give us these constant weight codes. But the paper also goes into proving that this method actually achieves polarization.
Right. That's essential for making sure these codes actually work well for error correction.
Right. So are we ready to dive into the proof?
Absolutely. The proof is pretty neat. It's a 2-stage process, first proving what they call slow polarization, and then building on that to show fast polarization.
Okay, so like building a foundation and then putting up the building.
Yeah, perfect analogy.
All right, let's lay that foundation then. What's this slow polarization all about?
It basically shows that as we keep applying the polar transform, the entropy of certain bits in the sequence will converge towards either 0 or 1.
Okay, so it's like they're becoming more predictable.
Exactly. And they do it gradually, which is why it's called slow.
Okay, got it. And how do they actually prove that happens?
It's a series of lemmas, each building on the last one. It all starts with lemma 3, which actually talks about coin flips.
Coin flips. Now we're really getting abstract.
Well, it's a clever way to analyze the entropy of a sequence and relate it back to what's happening with our Markov chain.
Okay, I'm trusting you here. So we start with coin flips, and what's next?
Lemma 4 brings us back to the Markov chain and talks about its stationary distribution.
Right, that's like the equilibrium state.
Exactly. The lemma shows that there's a minimum positive probability for states that are a certain distance apart in the chain.
Okay, and why is that important?
Because we need to make sure that all the states have a chance of being explored. If those probabilities were to get too small, the chain might get stuck and we wouldn't achieve polarization.
Right, it's got to keep moving.
Exactly. Then lemma 5 introduces 2 important entropy values, U and V.
Okay, more symbols to keep track of. What are those?
Well, U represents the entropy of 2 consecutive bits, and V represents the average entropy of each bit individually.
Okay, so one's a combined measure and one's individual.
Right, and the lemma proves that U is always greater than or equal to V.
So the combined entropy is at least as big as the average of the individual ones.
Yeah.
Makes sense, I guess. Okay, so what's next?
Lemma 6 is where we really see the periodic nature of the chain come into play.
Oh, how so?
Well, it says that for certain lengths and entropy values, you can always find 3 consecutive states where there's a significant difference between U and V.
So those entropy values are being pulled apart.
Exactly. And the size of the gap depends on a parameter in which we get to choose.
Okay, interesting. So we've got this gap between U and V. What do we do with that?
Well, Corollary 7 builds on that and shows that under certain conditions, the difference between 2 specific entropy values, denoted as HUO and HUO, is also always greater than some positive value.
Hold on, back up. What are those again?
They're just 2 slightly different ways to measure the entropy of a bit.
Okay, so they're both entropy measures, but they're diverging.
Right, that's the key.
Okay, I'm following. Now, we need to know what these entropy values are converging towards.
Exactly. And that's where lemma 8 comes in. It proves that the limiting value can only be either 0 or 1.
So the bits are settling into a definite state.
Precisely. Slow polarization.
Okay, we're almost there, I think. What's the last piece of this slow polarization proof?
Lemma 9. It essentially proves that no matter where you start on the chain, the overall entropy rate is the same.
Oh, that makes sense. Okay, so we've got all these lemmas like little puzzle pieces. How do they fit together to actually prove slow polarization?
Proposition 10 is what brings it all together. It uses all the insights from the lemmas to show that as the sequence gets longer, the proportion of bits with entropy less than ein converges to a certain limit.
And what is that limit?
It's 1 minus the entropy rate of the process.
Okay, cool. So we've got the bits separating out, some with entropy closer to 0, some closer to 1.
Exactly. That's slow polarization in a nutshell.
Great. So foundation laid. Now what about that skyscraper, that fast polarization?
That's where things get even more interesting. We're going to see how the convergence to 0 and 1 actually happens exponentially fast.
Wow, so the bits make up their minds much faster.
You got it. And that means we can have shorter codes, faster encoding, and faster decoding.
Now you're speaking my language. So how do they prove that?
Well, it involves a few new parameters and a whole bunch more inequalities, but I promise it's worth it. So, to kick things off with fast polarization, we got to talk about this new parameter they introduced. It's called A, and it's defined in equation 32.
Another Greek letter, huh? Okay, what does that one do?
Well, it basically sets a lower bound on the probability of certain events happening in our Markov chain.
So it's like a safety net, making sure those probabilities don't just disappear.
Yeah, that's a good way to think about it. And it's super important for fast polarization because it helps us control how those probabilities change as the sequence gets longer.
Okay, I'm starting to see the connection. So how does this help us with that control?
Well, it lets us relate the probabilities of things happening together to their individual probabilities.
So we can break down these complex events into simpler pieces.
Exactly. It makes the whole proof much easier to manage.
Okay, that makes sense. And I see they formalize that with lemma 11.
Right. It gives us an inequality that connects those joint probabilities and individual probabilities using the parameter.
Okay, cool. So we've got our probability inequality. Now what?
Now we get to introduce the Bhattacharyya parameters. They're denoted by Zemura and Placet.
Bhattacharyya parameters. That's a mouthful.
Yeah, I know. But they're basically a way to measure how different two probability distributions are.
Different. How do you measure how different distributions are?
Think of it like a distance. If the Potcast parameter is close to 0, it means the distributions are very similar, almost overlapping. But if it's closer to 1, they're very different, like they're pushing each other away.
Okay, I see. So a small distance means the distributions are almost the same, and a large distance means they're very distinct.
Exactly. And lemma 12 uses these parameters to prove two important inequalities.
Hit me with those inequalities.
The first one says that A, which measures the distance between the distributions of two consecutive bits, is less than or equal to a constant times, which measures the distance for a single bit. And the second inequality says that plus is less than or equal to a constant times is squared.
Okay, so we're basically setting up some boundaries on how these distances can change.
Right. As we apply the polar transform, these inequalities tell us how those distances evolve. Some of them shrink really fast, which is what we want for fast polarization.
Because that shrinking means the bits are becoming more certain.
Exactly. Less random, less entropy. Okay, then we have lemma 13.
Okay, what does that one do?
It brings in another set of parameters and plus key, which are kind of similar to the Bhattacharyya parameters, but they give us a slightly different perspective on how the entropy changes.
Okay, so like a different angle on the same problem.
Yeah, exactly. And it proves two more inequalities, showing that is less than or equal to a constant times squared, and plus is less than or equal to a constant times const.
All right, so we've got all these parameters and inequalities flying around. How does this all come together to prove fast polarization?
Well, that's where proposition 14 steps in. It's like the grand finale. It takes all those lemmas and combines them with a really powerful result from another paper, proposition 49.
Oh, so we're bringing in outside help.
Yep. And this proposition 49 helps us translate those inequalities into a statement about how quickly the entropy converges to 0 or 1.
So it's like the key that unlocks the whole thing.
Pretty much. It proves that the probability of those entropy values being close to either 0 or 1 increases super fast exponentially as the sequence length grows.
Wow. Okay, so that's fast polarization. We went from slow and steady to warp speed.
You got it. But hold on, we're not quite done yet. We still need to connect this back to the main result, theorem 1.
Oh, right. Theorem 1. What was that all about again?
It says that fast polarization happens even when we put those extra constraints on the initial and final states.
Right. So this proposition 14 is great, but it only works for that specific event, which only fixes the initial phase.
Exactly. Theorem 1 takes it further to a more general case where we fix both the initial and final states. And to get there, they introduce this new constant b.
Another constant. All right, I'm trying to keep up. What does b do?
B is our connection between the fast polarization we've already proven and the more general case we want to prove.
Okay, how so?
Well, the proof shows there's a b greater than 0 no matter what the sequence length or other parameters are, such that two specific inequalities hold.
And those inequalities tell us?
They tell us that even though the event in Theorem 1 is more restrictive, the way our parameters behave is still similar to how they behave under theorem, just scaled by that constant b.
Okay, so even with those extra constraints, the fast polarization is still there, just maybe a little different in magnitude.
Exactly. And proving those inequalities is really important because it lets us take all that work we did for it and apply it too.
So it's like we're building a bridge between those two cases.
Perfect analogy.
Okay, so how do we actually prove those inequalities? They seem pretty complex.
It all comes down to lemma 15 again. It's our secret weapon. We use it to break down the probabilities and entropies under both and then rearrange things until we get those inequalities.
So it's like a mathematical jigsaw puzzle.
Kind of. And the value of B depends on a few things, like the minimum probability for any state in the chain, and that value from the factorization of the period.
Okay, so B is not just some random number. It's tied to the structure of the chain.
Right. And the proof of the second inequality, inequality 50, uses a similar strategy but with a slightly different approach. Instead of two new events, it defines a whole bunch of them, each representing a different combination of initial and final states.
So we're basically covering all our bases.
Exactly. And once we have both of those inequalities proven, the rest of the proof for Theorem 1 is pretty straightforward. We just use those inequalities and what we already know about to show that fast polarization happens under 2.
Okay, so we finally made it. We've got fast polarization, even with those extra constraints.
You got it. Theorem 1 proven.
I feel like we just climbed a mountain.
It was a tough one, but the view from the top is worth it.
So now that we've proven these codes can achieve fast polarization, are they actually practical? Can we actually use them?
Okay, so Theorem 1, right? This is where we really prove that fast polarization happens even when we restrict those initial and final states of our Markov chain.
Yeah, like we're getting even more specific with our control, not just the starting point, but the end point too.
Exactly. And the whole proof hinges on how periodic the chain is, those phases, and all those inequalities we worked out before.
Okay, my brain is ready for round 3. Where do we even start with a proof like this?
Well, we got to remember how that period P breaks down, right? It's the product of D and Q, where D is a power of 2 and Q is odd.
Right, like factoring it out. But why does that matter so much here?
Because it helps us see the cycles in the chain. We can group states based on their phase modulo D. That helps us figure out how the probabilities change over time.
Okay, so it's like a roadmap, highlighting those key points that guide where the probabilities go.
Yeah, good analogy. And remember I, that's the common phase for all the states in our initial set, D. So then we define I as I modulo D. Basically, it tells us which phase class our initial state belongs to.
So I is like zeroing in on where we start based on those phase classes. Okay, but how do we actually use all this to show fast polarization with these constraints?
Well, the trick is to connect what we already know about, the event where we fix the initial phase modulo D, to our target event, which has that extra final state constraint.
Right, because Proposition 14 already showed us we get fast polarization for Lion.
Exactly. The entropy goes to 0 or 1 really quickly. So if we can show a clear relationship between the parameters under both events, we can extend those results to 2.
Okay, I'm with you. So how do we build that bridge between the two?
By introducing this constant value, B. It's a scaling factor that links the behavior of those parameters under both events.
Another constant. All right, I'm trying to keep up. What does B actually do?
The proof shows there's a B greater than 0, and it doesn't depend on the sequence length or anything else, such that 2 really important inequalities hold.
Okay, hit me with those inequalities. Why are they so crucial for proving Theorem 1?
There are equations 49 and 50 in the paper. Basically, they set a boundary between the Bhattacharyya parameters and entropy measures under both SLAY and LAY. They tell us that even though it's more restrictive, those parameters under are still kind of similar to how they behave under Fegley, just scaled by B.
Okay, so even with that extra constraint, the fast polarization is still there, just maybe a bit different in how strong it is.
Exactly. And proving these inequalities is the big hurdle, because then we can just apply all the fast polarization stuff from...
It's like we're saying that the fast polarization effect is strong enough to handle those extra constraints.
Right. But actually proving the inequalities is tough. It all boils down to lemma 15 again.
Ah, our trusty lemma.
We use it to break down the probabilities and entropies under both eng and com. Then it's just clever rearranging until those inequalities pop out.
Like a mathematical magic trick.
Haha, kind of. And that B value, it actually depends on the minimum probability for any state in the chain, they call it, and that mulled from factoring the period.
So it's not arbitrary, it's tied to the core of our Markov chain.
Yep. And proving the second inequality, inequality 50, uses a similar idea but a slightly different tactic. Instead of just 2 new events, they define a bunch of them, each with a different combo of initial and final states.
So covering all the possibilities, making sure it works no matter what the specific states are.
Exactly. And once those inequalities are proven, the final part of proving Theorem 1 is easy. We just use those inequalities and what we already know about to show fast polarization happens under 2.
We did it. We got there. Fast polarization, even with those extra constraints.
Theorem 1, officially proven.
This whole deep dive has been amazing. We started with this seemingly simple idea of using Markov chains for these codes, and it's led to some really powerful results.
It really shows you how elegant math can be, and how even super abstract stuff like this connects to real-world problems.
Absolutely. Constant weight polar codes have so much potential. It's exciting to think about how they could change things in areas like optical communications and DNA storage. Definitely.
Yeah.
And for anyone who wants to go even deeper, we highly recommend checking out the full paper, Constant Weight Polar Codes through Periodic Markov Processes.
It's a challenging read, but so worth it for anyone who really wants to dive into the details. So to everyone listening, thank you so much for joining us on this incredible journey. We hope you learned something new and had some fun along the way. Keep exploring, keep learning, and we'll catch you on our next deep dive.